Hi everyone, welcome to Go Classes. In this lecture, we will study I/O interfacing, input-output organization, and also interrupts. Okay, so these concepts we will study in this lecture. Let me tell you that our focus will be on understanding these concepts in a correct way, in a very crystal clear way. Okay, because these concepts, let me tell you, like DMA, I/O interfacing, okay, so programmed IO, interrupt driven IO, so these concepts are very misunderstood concepts. So our focus will be on correct, clear, and complete understanding of these concepts. Okay, so let's start the session now. First we will discuss what are IO devices. What are these input output devices? I means input, O means output. So what are IO devices, input output devices? You already know intuitively what are IO devices. These are also called peripherals. So peripheral IO devices, these are same. For example, keyboard, mouse, printer, microphone, monitor, speaker, hard disk. Okay, all these are IO devices. Your hard disk, that is also IO device. Okay, keyboard, mouse, all these are IO devices. These are also called peripherals, remember. Now, let me tell you that there are two type of IO devices. One is input device, one is output device. You can see IO device. I means input, O means output. Okay. So first of all, what is a IO device? The definition is like this: that these are hardware components, okay, through which the computer, the CPU, can interact with the external world. Okay, so you can see IO devices or peripherals. These are hardware components that enable a computer system, a CPU, to interact with the external world. For example, the user can give input, right? Yes or no? You with the help of keyboard, I can give input, and the CPU can give output to the user. Okay, for example, on the monitor, okay, the CPU can write something, so you can easily see that IO devices means input and output devices. The user can give input to the CPU and the CPU can give output to the user. Okay, so this is very simple definition. IO devices, these are hardware components that through which the computer system can interact with the external world. External world, for example, I can say user. Okay. Now there are two type of IO devices. One is, remember, depending on are they input or are they output. So you can see IO devices, either they are input devices, means they can give, user can give input to the computer. Okay, so IO devices, they can be input devices, for example, your keyboard, your mouse. Okay, user can give input to the computer. Or they can be output devices, for example, your monitor, your speaker, means the computer is giving output to the user. Okay, or remember, it is also possible that there is IO devices which is both input and output. So you can see IO devices, either they send data to the computer or they receive data from the computer. Okay, and sometimes both. So let's see examples. Let's see what are the type of IO devices. One is input device. Input device means user can give input to the computer. So devices that allow the user to send data, send commands to the computer. For example, keyboard, mouse, microphone. Yes or no? So you can easily see, for example, this microphone right now, you can see. So through this microphone, I am able to input. I am able to give input to the computer. Okay, so you can see input devices means user is giving input to the computer. For example, okay, keyboard, mouse, microphone. Now there is output devices. Output devices means the computer is giving output to the user. Okay, devices that display or output data from the computer to the user. For example, your speaker, for example, printer, projector, monitor. So these are output devices. Now there are some devices which are input as well as output. Okay, means can anyone suggest one device which is input as well as output? See, speaker is output device because the computer will give output on the speaker to the user. So speaker is output device. Okay. Now, can anyone suggest one device which is both input and output device? Can anyone suggest? That is your hard drive. Yes or no? So you can see hard drive. You can see through hard drive, you can give input to the computer. Also, the computer can give data to the hard drive. Yes or no? The computer can store data to the hard drive. For example, your pen drive. Yes or no? So pen drive is also input output device. So you can see input output device. That means these devices, they can send data to the computer or they can receive data from the computer. So they can send data to the computer or they can receive data from the computer. Like for example, your hard drive, your pen drive. Yes or no? For example, USB flash drive. So these are the examples. Now, now we will study what is a IO interface. So we have already seen what is IO device. Now we will see what is IO interface, or I can say IO module, or you can call it IO interface. So let's see what is this IO interface. Okay. Now, before we study what is IO interface, what this means, before we study, let me ask you one question. That is, we know how CPU and main memory connected directly via system bus. Okay, you already know that CPU and memory, they are connected via system bus. Similarly, can we connect peripherals, means IO devices, directly to the system bus? Did you understand the question? See, we already know how the CPU and memory, they are connected. So you can see there is a system bus. In this system bus, we have control bus, address bus, and data bus. So this system bus, through this system bus, or I can say via this system bus, you can see CPU and memory, they are directly connected. Yes or no? CPU, memory, they are connected via this system bus. Okay. And how they interact with each other, that also you know. How CPU will interact with memory, that you already know. Okay. What will happen? You know that this system bus has control bus, address bus. Okay, in this system bus, what we have address bus. Okay, so we have address bus, we have data bus, we have data lines, and we have control lines. Okay, yes or no? So you can see in this system bus we have address lines, data lines, control lines. Now, how the CPU will interact with memory? What will happen? Very simple. This CPU will generate this address. Yes or no? So this CPU will generate the address of memory cell. Now, that address, this CPU will put on the address lines. Okay. And for example, let's assume CPU wants to read from memory. Okay. From memory, CPU wants to read. Then what this CPU will do? This CPU will put read signal on the control line. Okay. And then what will happen? Now you can see when the CPU will put address on the address lines. Okay. Then you can see that cell will be activated in the memory. That location will be activated. Okay, and you can see on the control line we are putting read signal, CPU is putting read signal. So what will happen? That data in that location, in that memory location, the data will come on data bus, and it will come to the CPU. Yes or no? Okay, very simple. So this is how CPU and memory, they interact with each other. Okay, that is the interaction between CPU and memory. So you already know that CPU and main memory, they are connected directly by system bus. Okay. Now my question is, can we connect IO devices directly to the system bus? Let me know. Can we connect these peripherals directly to the system bus? Let me tell you, the answer is no. See, my question is like this. For example, this is your system bus. Okay, let me create. Let's assume this is our system bus. So this is the system bus. In system bus, we have address bus, data bus, control bus. Okay, so you can see this is our system bus. Now, okay, via this system bus, you can see that CPU and main memory, they are directly connected via this system bus. This is your main memory. Now, can we connect the IO device directly? For example, can I directly connect the mouse here? Can I directly connect the keyboard here? Let me know. So using this system bus, can I connect the keyboard directly to the system bus? Means, can I connect this mouse directly to the system bus? This is what I'm asking. That can we do this? Let me tell you, the answer is no. Okay, we cannot do this. Okay, see, main memory, we are connecting directly to the system bus. Okay, CPU, we are connecting directly to the system bus. But I'm asking your IO devices, keyboard, mouse, hard drive. Okay, so all these IO devices, can we connect directly to the system bus? The answer is no. Okay, we cannot do like this. Okay, so let me tell you, the answer is no. Now, what are the issues? We cannot connect like this. So I can say directly like this, we cannot connect. Okay, so now what are the reasons, or I can say what are the issues? If we directly connect, then what are the issues? So let me tell you that why we cannot connect. Remember, we cannot connect these IO devices, these peripherals, directly to the system bus. The reasons or the issues are as follows. What is the first reason? The first reason is there are many different variety of peripherals, like mouse, keyboard, disk, printer, speaker, microphone. Okay, so you can easily see there are many variety of peripherals that we have, and they have different speed. All of them have different speed. For example, mouse and keyboard, they are very slow. Okay, yes or no? Tell me, how many characters can you press in 1 second on the keyboard? When you are typing, how many characters, how many buttons can you press in 1 second? Maybe 10 buttons if you are very fast. Okay, if the user is very fast, maybe 10 buttons. Still it is very slow, because remember, CPU is very fast. CPU can execute millions of instructions per second. Okay, yes or no? So you can easily see that CPU is very fast, and these IO devices, they have, I can say, widely varying speed. For example, mouse and keyboard, they are very slow. Disk is actually comparatively fast. Disk is faster than mouse and keyboard. Okay, yes or no? So you can see there are many different variety of IO devices, and they have different speeds. Okay, so if you directly connect them, like this keyboard, mouse, disk, okay, all of them, if you directly connect, then you can see they have a lot of variation in their speed. Okay, so that is the reason it is, I can say, the CPU will have to handle, okay, these variations in the speed. If you directly connect all the devices, if you directly connect to the system bus, then remember there will be no, I can say, standardization, because there they have variations in the speeds. Okay, huge variations in the speed. Now let me tell you one thing. Why we connect main memory to the system bus directly? What is the reason? Can anyone tell me? What is the reason that we can connect main memory to the system bus directly? Because see, main memory, we already know the speed of main memory. Yes or no? The speed of main memory is already known to us. You have seen in many questions that this is the access time of main memory. Yes or no? Do you agree? So you can see the main memory access time, or I can say the speed of main memory, that is already known to us. So that is the reason there are no fluctuations. There is no variations of speed when we have main memory. If you have, let's assume, multiple main memory modules. For example, let's assume this is your main memory module M0, this is your main memory module M1, this is your main memory module M2. Okay, let's assume this is, for example, let's assume 16 KB. This is 16 KB main memory. Okay, this is also 16 KB main memory, this is also 16 KB main memory. So you can easily see that when you have main memory modules, then their speed does not vary. Yes or no? Their speeds are already known to us, they do not fluctuate, or I can say they are almost, I can say, the, I can say, approximately we already know the speed of main memory. So that is the reason we can connect main memory to the system bus directly. Okay, because the speed of main memory is already known to us. Okay, is this clear? So you can see one reason because why we cannot connect IO devices directly to the system bus. The one reason, that is data transfer rate of different IO devices that vary too much. Okay, you can see we have slow IO devices. For example, mouse, keyboard, they are very slow. Okay, disk is actually more, disk is faster than this keyboard and mouse. Okay, so you can see different peripherals, there are many different type of peripherals, and they have different data transfer rate. So that is the reason this is one of the issue. This type of, I can say, variation in the speed that can create issue. So that is one of the issue. Let me tell you another issue, that is data transfer rate can be regular or irregular. What that means? This is another issue, that data transfer rate of peripherals, that can be regular or irregular. For example, when you press the button on the keyboard, okay, now the CPU does not know when you will press the next button. Yes or no? Maybe I can press the next button in 1 second, or maybe I will press the next button in 1 hour. Yes or no? So you can see for the keyboard or for the mouse, you can see the data transfer rate that will be irregular. Do you agree with me? But you can see the hard drive, the hard disk, that will have, I can say, regular data transfer rate. Okay, from the hard drive, what you can do, you can basically, you can fetch a lot of data, maybe 10 KB, maybe 100 KB data you can fetch from the hard drive. So you can see data transfer rate, that is regular or irregular for different IO devices. Okay, for example, your keyboard and mouse, they have irregular data transfer rate. Yes or no? I don't know, the CPU does not know when you will press the next keyboard button. Yes or no? So you can see, so this is another issue. Now what is another issue? Let me tell you. The another issue is size of data blocks that are transferred at a time, that also varies widely. Okay, for example, tell me, from the disk, at a time, how much data you can bring? How much data means, I am asking the size of data blocks, so that you can transfer at a time. So from the disk, maybe you can bring, maybe I can say, almost I can say 10 KB data. Okay, let's assume. Okay, so I'm assuming that you can bring maybe 100 KB data at a time. Yes or no? 100 KB data at a time you can bring from the hard drive at a time. But you can see when you press a button on the keyboard, then only one byte is transferred. Yes or no? Agree? So when I press on the button, on the keyboard, when I press a button, then it simply means one character is transferred. One character means one byte. Agree? So when I press a button on the keyboard, then one byte is transferred. Yes or no? So you can see the keyboard, the size of data blocks that are transferred, okay, by keyboard, that is only one byte. But the hard drive, the hard disk, that will give you maybe 10 KB data, maybe 100 KB data at a time. So you can see that the size of data that is transferred at a time, that also varies widely. Okay, that can be few bytes to kilobytes. Do you agree? So far, all the issues, are you understanding? Basically, all the issues are because of many different variety of peripherals, many different variety of IO devices we have, and they have different characteristic. Yes or no? We have mouse, keyboard, disk. Okay, we have our printer, projector, our microphone. So many different type of peripherals, many different type of IO devices we have, and they have many different characteristic. Yes or no? So far, all the three reasons did you understand? All the three issues did you understand, that they have different characteristics? Okay, yes or no? Now let's see the another issue. Now tell me one more thing. What about the size of data block from main memory? I told you that main memory is connected to the system bus directly. Okay. Now in the main memory, is there any issue of size of data block that is transferred? Tell me, in the main memory, is there any issue? No, there is no issue, because in the main memory, what you will do? In main memory, you will transfer one word at a time. So that is fixed. Yes or no? Yes or no? In the main memory, what the CPU will do? Basically, one word will be transferred at a time. So that is fixed. Okay, yes or no? That is the reason. Remember, main memory we can connect directly to the system bus. Okay, but these peripherals, they have different characteristics. So that is the reason we cannot connect them directly to the system bus. So these three reasons so far, did you understand? Let me know. Let me tell you another reason, that is they have different characteristics. Yes or no? Different IO devices, they exhibit different characteristics. Okay, they have different data format also. Different IO devices, they have different data format. For example, your disk, your hard disk, okay, that will store the data in form of magnetism. Okay, yes or no? So you can easily see different IO devices, they use different data formats. Okay, they may not use binary. Okay, your main memory, that will use binary 0101 binary, but you can see different IO devices, they have their own data formats. Okay, agree? So you can see these are the reasons because of which we cannot connect these IO devices directly to the system bus. Please tell me, did you understand? Let me know. So far, all the points, are they clear? So again, I'm telling you that your main memory, that is directly connected to the system bus. Okay, the reason is very simple, because main memory does not have, I can say, variation in the speeds. The speed of main memory is already known to us. Okay, and also the second point, how much data will be transferred from main memory at a time, that you already know, that is one word. Okay, one word of data will be transferred at a time. So you can see that the main memory characteristic, they are already known to us. But you can see the peripherals, the IO devices, there are so many IO devices, and all of them have different characteristics. Yes or no? So their data transfer rates are different, their how much data will be transferred at a time, that is different. Okay, yes or no? Now they can have data transfer regular, irregular, that is also another issue. Data format is another issue. Yes or no? So these are many different issues, because of which we cannot connect the IO devices directly to the CPU, directly to the system bus. Okay, so what we need? So we need some interfacing. Okay, we need some kind of interfacing. So let me tell you that you cannot connect. You can see these are IO devices. Let's assume, for example, mouse, keyboard. Okay, these IO devices you have. So you cannot connect them directly to the system bus. So what we need? We need some kind of interface. We need some kind of interface. We need. Okay, is this clear? So the point is this, that this is your system bus. Now let me tell you that this is your system bus. This is the system bus. Now to the system bus, we cannot connect any device directly. So what we do? We need some interface. Okay, we need some interface. We need. So this is our device interface. We need some interface. Remember, some interface we need, and this IO device will be connected to this interface. For example, let's assume you have keyboard. For example, let's assume you have keyboard. Now this keyboard will be connected to this interface. Okay, or I can say that for this keyboard, this device interface, I can call it keyboard device interface. Okay, is this clear? So very simple point, that this keyboard I cannot directly connect to the system bus. So we need some kind of interface. We need, yes or no? We need this interface. So this interface will be connected to the system bus, and this keyboard, this input output device will be connected to the to the interface. Okay, now what this interface will do? This interface will handle all these variations. I told you there are some variations. Yes or no? The different characteristics. Yes or no? So the peripherals, they have different properties. Now remember, this interface will take care of all the variations. Okay, so remember, this will take care, the responsibility of interface, that is to, this will take care all the variations in the speed, all the variations in the properties, all the variations in the characteristics. Okay, so remember, this will take care of all variations, all variations in device characteristics. Okay, is this clear? So that is the reason we need some kind of interface. Now we will see what this interface has. Means inside this interface, what do we have? But did you understand what is the interface? Let me know. Okay, again, I'm repeating that we cannot directly connect this IO device to the system bus. So we need some kind of interface. Okay, that is the reason. So now we will study what is inside this interface. So I've already written here. You can see inside this interface, what we have. Inside this, we have device controller. Okay, this is your interface. So you can see there is system bus. So here we have system bus. Now there is our interface. Okay, this is our device interface. And the device is connected where? The device is connected to this interface. Okay, the actual device, your mouse, keyboard, printer, that will be connected here. Okay, this is your actual IO device. Okay, so very simple. Now let's see what is inside this interface. What do we have inside this interface? So let me tell you, inside this interface we have device controller. Actually, let me tell you, in this interface we have two things. Inside this interface there are two things. One is related to this IO device. Okay, basically we want to handle the characteristic of the IO device. Do you agree? I told you that this interface, it will take care of all the variations in the device characteristics. Agree? Yes or no? Basically, for example, speed, okay, and data format. Yes or no? So you can see there are different characteristics of IO devices. So I told you that this interface will take care of all of them. So you can see this interface has two things. Let me tell you. One is, I can say, for example, this part. This part will handle the properties of the IO device. For example, the data format and all these things. Okay. So anyway, we don't care about this thing. I can say here we will take care of device properties. Okay, is this clear? So here we will take care of device properties. Okay, but there is another part, that is device controller. So you can see inside this device interface there is device controller. Okay, here this is our device controller. Okay, in this device controller what we have? So I can say that, for example, this one. Okay, I can say this part, this is your device controller. Now we need to study what is this device controller. Okay, this is our main, I can say, topic to study, that what we have inside this device controller. But so far, did you understand? Let me know. So far, did you understand that? Very simple point. IO device we cannot connect directly to the system bus, so we need this interface. I told you that interface will take care of all the variations in the properties of IO devices. Yes or no? So you can see this interface will have two things. Let me tell you. One is this part, or I can say this, this part of the interface, this will take care of the data format, all these things. Okay, we don't care about it. Now we are interested in what this device controller has. Okay, so let's see what this device controller will have. Okay, so let's focus on device controller. So I can say that in this interface, this is the device interface. In this device interface we have device controller. This is our device controller. Now, what do we have inside this device controller? So let me tell you, very simple. In this device controller, what we have, let's understand. First of all, we have address. Every device will also have an address. Yes or no? See how CPU will communicate with memory. There will be address. Okay, the memory location. So that address of that memory location will be there. Yes or no? Similarly, every device also has an address. Every IO device, your mouse, your keyboard, your hard drive. Okay, all these devices, all these IO devices, they also have an address. Okay, so what we need, the CPU will generate the IO address. So that is the reason, first of all, we need address decoder. Yes or no? In this device controller, what we need? We need address decoder. Okay, this is one of the things that we will have in this device controller, that is address decoder. Okay, what else we will have? Why we need address decoder? Please tell me. Because very simple, that every IO device has an address. Okay, so let's assume CPU wants to communicate with keyboard. Then CPU will generate the keyboard address. Is this clear? CPU will generate keyboard address if the CPU wants to communicate with keyboard. So you can see there is a address decoder, okay, for IO devices addresses. Now what else we have? Now I told you already that let's assume this is your keyboard. Okay, let's assume this is the keyboard interface. For a moment, let's assume this is your keyboard interface. Now tell me, let's assume that I press one key at per second. Okay, this is the keyboard interface, and let's assume this is the actual keyboard that I've connected here. This is the actual keyboard that I connected here. Now let's assume that this keyboard, using this keyboard, I'm the user, I'm pressing one key 1 second. Okay, means okay, I'm pressing one button per second. 1 second, one button I'm pressing. Now tell me one thing. Just tell me one thing. Okay, or maybe you can assume something else. Okay, this device you can assume. Let's assume this is giving one bit at a time. Okay, let's assume this is giving one bit at a time. This is device. This is some IO device, and let's assume this is providing one bit at a time. Okay, this is IO device. Now, what I'm saying, I am saying that this is generating. This IO device is generating one bit at a time, one bit per second at a time, or I can say one bit at a time. If this device is generating one bit at a time, then tell me, will you send this one bit on the system bus? Just tell me this question. A very simple question I'm asking, that if this device, this is IO device, let's assume this is generating one bit at a time, this is generating. For example, using your keyboard, at a time, how many bits you can generate? Using the keyboard, you can press the button. Okay, one button means one character, means 8 bits. Yes or no, one byte. Agree? So using the keyboard, at a time you can generate 8 bits. Do you agree with me? Okay, the hard drive can generate more bits. At a time, the hard drive can generate kilobytes. Okay, but the keyboard can generate only 1 byte. Now let's assume there is another IO device, there is some other IO device, and let's assume that is generating one bit at a time. Okay, now tell me, when this IO device will generate one bit, will you send it to the CPU via the system bus? Please tell me, will you do that? No, you will not do that, because you are not utilizing the bus. Okay, in this bus, let's assume you have 16 data lines. Then you are only putting one bit on the data lines. There are 16 data lines, and you are putting only one bit on the data lines. Then that is, I can say, you are not utilizing the bandwidth. Agree with me? Okay, so that is what I'm saying, that this device, let's assume this is generating one bit at a time. Then we will not send this one bit directly. Yes or no? What we will do? Can anyone tell me what we should do in this type of situation? This is providing one bit at a time. We do not want to send one bit to the CPU, okay, because we want to utilize this system bus. Yes or no? In this system bus, let's assume there are 16 bits. Data line has, there are 16 data lines. Okay, then in this situation, what we will do? We need a buffer. Do you agree? We need a buffer. This interface will need a buffer. Okay, this needs a buffer, or I can say data register. Okay, we will need data register. Do you agree? So this buffer, or I can say this data register, we need. What we will do, what this buffer will do, this buffer will, okay, this will, I can say, assemble the 16 bits. This will assemble the 16 bits. Okay, 16 bits means one bit at a time. So this buffer, we will collect 16 bits here. Then once the 16 bits are collected, then we will send to the CPU. Agree with me? Is this point clear? Why we use the buffer? Is this point clear? In this device interface, or I can say in this device controller, why we use the buffer, why we use this data register or buffer, what is the reason? Did you understand? Very simple. This IO device is very slow. This is generating one bit at a time. We don't want to send this one bit to the CPU, okay, because we want to utilize the system bus. Okay, so what we can do, we can have this buffer or data register in the device interface, in the device controller. We can have this buffer. Okay, maybe this buffer can be, for example, 16 bits. This buffer size, this can be, let's assume, 16 bits. Then what this buffer will do, what this interface will do, it will collect 16 bits. Once the 16 bits are collected, then the interface will send these 16 bits to the CPU. Okay, so that is the reason we need buffer. Now what else we need? Can anyone tell me what else we need? So let me tell you, we need something called status register. We need something called status register. Now what is the reason? Now, what is the reason? Let me tell you the reason. Let's assume CPU wants the data from this IO device. Okay, from this particular IO device, the CPU wants data. Maybe this is mouse. Maybe this is mouse. Okay. Now let's assume the CPU. There is CPU here, and the CPU wants data from this IO device. Then what the CPU will do? This CPU will interact with the interface. Remember, the CPU will not communicate with the IO device. The CPU will communicate with the interface of this IO device. This IO device, this mouse, this has this interface. Okay. Now, very simple. This CPU wants data from the mouse. From this mouse, we want data. Then what this CPU will do? This CPU will communicate with the interface. This CPU will not communicate with the IO device, because there is interface. You can see in between system bus and IO device, there is interface. So this CPU, what it will do? It will communicate with the interface. Okay. Now let's assume the CPU command is coming. Okay. CPU is giving command to the interface that I need data from this IO device, from this mouse, I need data. Then what this interface will say? This interface will say data is not ready. Do you agree? Initially, data is not ready. Yes or no? Data that is not ready. So then what this interface will do? It will collect data. Okay, one bit at a time, one bit at a time. So you can see in this buffer, it will collect data. Okay, so you can see after 16 time units, the data will be collected. And then this interface, what it will do? It will make the status register. In the status register, there are many bits. In this status register, it will make, for example, let's assume this bit. Let's assume this bit indicates status, means ready or not, means the data is ready or not. Okay, is this clear? In this status register, let's assume this bit indicates whether the data is ready or not. Now, when the data is ready in the buffer, in this buffer, once the 16 bits are ready, then this interface will make it 1. Okay, then the CPU will know, okay, the data is ready. Now remember, when data is not ready, then this status, I can say this will be 0. This CPU will see this 0 and it will see, okay, the data is not ready. But when the data is ready in the buffer, then this status register, this will contain this 1. Okay, is this point clear? Very simple point. Agree? So that's it. This is what we have in the device interface. Is this point clear to everyone? Please tell me, did you understand? Very simple. In the device interface, what we have? We have three things. Remember, in the device controller, mainly we have three things in this device interface. This is the device interface. In this device interface, mainly we have three things, or I can say we will focus on three things. One is buffer. One is buffer, or you can call it data register, or you can call it data register. So we have this buffer. Why we have this buffer? Quickly tell me. Anyone? Why we have this buffer? Because remember, IO device is very slow. Yes or no? IO device is connected here. IO device is connected here. This is your IO device. Now IO device is very slow. So this IO device will not generate the data very fast. Yes or no? Maybe this IO device is generating one bit at a time. So because this IO device is very slow, so this IO interface, what it will do? This IO device interface, what it will do? It will collect the data. Okay, so that is the reason we need this buffer. Is this point clear? Because IO device is very slow. So that is the reason we will collect the data in this buffer. Okay, if this is generating one bit at a time, then, and let's assume this buffer size is 16 bits, then we will collect a 16 bits. Then those 16 bits we will send to the CPU. So this is the reason for buffer. Another, what we have? We have address decoder. Yes or no? Why we have address decoder? Please tell me. What is the reason we have address decoder? Because there are many IO devices, mouse, keyboard, disk, hard drive. So you can see there are many IO devices. Now they have different addresses. So that is the reason we need address decoder. Memory also has an address decoder. Do you remember? The memory also has an address decoder, the memory decoder. Yes or no? Similarly, this is IO address decoder. Okay, or I can say this is IO decoder. Okay, is this clear? Now, what another thing we have? Another thing we have, that is a status register. Yes or no? This is another thing that we have, status register. Okay, in this status register, remember there can be many bits. Okay, for example, there can be 8 bits. In this status register, there can be many bits. Okay, for example, this 8 bits you can have, and maybe this bit we are using for ready or not. Okay, device data ready or not. Device data ready or not. Okay, is this clear? Okay, so this is what we can do. Okay, let me know. So now you might be thinking, sir, in the status register, what these other bits are used? Why we are using the other bits? See, data is ready or not, for that one bit is required. Yes or no? Okay, if this is 0, for example, let's assume if this is 0, then it simply means data not ready. Okay, data not ready, device is not ready. Yes or no? Or I can say when this is 1, then it means data is ready. correct? So for that we only need one bit. Then why we are having the other bits? What is the reason for the other bits? The other bits can be used for other purpose. Okay, there can be some other purpose for the other bits. For example, let me give you one idea. Let's assume there is printer. What are the issues in a printer? Please tell me. Let's assume there is a printer. This printer you have. So this printer is connected to printer interface. Yes or no? So there will be printer interface. Okay, this is your printer interface. And remember, this will be connected to the system bus. Correct? This will be connected to the system bus. Yes or no? Now, this is the printer. Now tell me, what are the issues that can happen in a printer? In a printer, you have a status register. This is the status register in a printer. Now, I already told you that, for example, this bit you can use for data ready or not. Yes or no? Device ready or not. Okay, or I can say data, or I can say device is ready or not. So, for example, device, is that ready or not? Now, for that, we can use this bit. Okay, maybe this bit we are using paper is there or not. Yes or no? Okay, for example, maybe paper, out of paper. Okay, this bit can be used for indicates out of paper. This indicates out of paper. Yes or no? That is another issue. This can indicate out of paper. Agree? Is this clear? So this is what I'm saying. If this is 0, then it simply means we are not out of paper. And if this is 1, then that means we are out of paper. Okay, is this clear? So what I'm saying that there is a status register. In this status register, these bits are also used for different purpose depending on the IO device. Remember, there are many different IO devices. So depending on the IO device, we can use these bits for different purpose. Okay, but one of these bits is very important. You can see this particular bit. This is actually very important, and this tells us whether the data is ready or not. Okay, the device is ready or not to send the data or to receive the data. Remember, this device, this can be input device or this can be output device. Yes or no? So this bit, this particular bit, it will tell us whether the device is ready to send the data or is this ready to receive the data. So this particular bit is useful. Okay, and the remaining bits you can use for different purpose. I told you, for example, if your printer, then for example, this bit you can use to indicate out of paper. Okay, this bit you can use to indicate something else. This you can use to indicate something else. So that is the point. Is this point clear? All these simple points I am explaining, please tell me, are they clear? Let me know. So you can easily see we cannot connect the IO device to the system bus directly. So we need something called interface. Yes or no? So this IO device will be connected to the system bus via this interface. There is an interface. And in this interface, what we have? We have address decoder, we have data register, we have status register. Okay. And there is control circuit also. What this control circuit will do? Okay, this is for control signal. Okay, this is for control signal. For example, do we want to read the data, do we want to write the data? So this is for control signal. Anyway, don't worry, most of the time I'm going to use these things. Okay, data register and status register. Most of the time I will use these words like buffer, buffer, status. Okay, so I told you why we use buffer and I told you why we use status register. Okay, in this IO interface, these two things we will mainly use. Is this clear? So you can see this IO device, this is connected to the system bus. This is our system bus. Okay, so this IO device is connected to the system bus via IO interface, IO controller, or you can say IO interface. In this IO controller, in this device controller, we have these registers, data register, or I can call it buffer. We have status register, okay, and we have address decoder and we have command. Okay, is this clear? Let me know. So very simple point. Now remember, when the CPU want to interact with a particular IO device, then what this CPU will do? Then the CPU will generate the address of that IO device. Remember, every device has an address. Is this clear? Every device has an address. Every IO device has an address. So if the CPU wants to communicate with some IO device, then CPU will generate the address of that device. Okay, very simple point. Okay. Now, one more thing I told you, if CPU wants to communicate with mouse, then what the CPU will do? CPU will not communicate with mouse, CPU will communicate with mouse interface. Every device has an interface. So this is what I'm saying, that if CPU wants to communicate with the IO device, then it will not communicate directly to the IO device. It will communicate with the IO controller. It will communicate with the device controller. Is this point clear? Now, next, when the processor will issue a IO command, let's assume the processor want to communicate with mouse or keyboard or hard drive. Then the when the this processor, it will generate the address of that IO device. Okay, it will issue the IO command. Okay, and the command will contain the address of that device. All these points, are they clear? In the main memory, if I want to access some location, then what I will do, I will generate main memory address, CPU will generate main memory address. Similarly, if the CPU wants to communicate with some IO device, then the CPU will generate address of that IO device. Okay, is this clear? Every IO device has an address. Very simple. And remember, the CPU will not communicate with the IO device directly. CPU will communicate with the device controller, or I can say CPU will communicate with the interface. The CPU will communicate with the IO device interface. It will not communicate with the IO device directly. Very simple. Now let's see what is IO port. So far we have seen two concepts. Are they clear? We have seen what is IO device, what is the definition of IO device, different type of IO devices, input devices, output devices, and some devices which are both input and output. So this is what we have seen. Then we have seen what is IO interface. I told you that IO devices cannot be connected directly to the system bus. Why? Because we have many different type of IO devices and they have different properties. They have different characteristics. So that is the reason we cannot connect IO devices, peripherals directly to the system bus. So what we need some kind of interface. Then I told you that what we have inside this interface. Inside this interface, we have a status register so that we can find out whether the data is ready or not, whether the device is ready or not. Is the IO device ready to receive the data, or is the IO device ready to send the data? Okay, yes or no? So we need this status register in the IO interface. In the interface, we need buffer also, I told you, because IO devices are very slow. So they will generate the data very slowly. So we need buffer so that we can collect the data. Okay, we can collect enough data, we can collect, and that data we can transfer on the system bus, on the data lines, we can transfer that data. Okay, also we have address decoder because every IO device has an address. Yes or no? So if you want to communicate with keyboard, then what the CPU will do, then the CPU will generate the keyboard address. So very simple, all the concepts so far. Now let's see what is IO port, what is the definition of IO port. Okay, in your computer, in your laptop, what is a port? Tell me, anyone want to tell me? In your daily life you use this word port, USB port, yes or no? In your daily life, in your computer, in your laptop, you use this word USB port. So similarly, what is IO port? So let's see the definition. The IO port, that is the physical point at which the device is connected to the computer. Okay, see this, read this definition, and then you relate this definition with your USB port. In your laptop there is a USB port, yes or no? Pen drive port, correct? Okay, so you can see, read this definition. What is IO port? That is the physical point at which the device is connected to the computer. That is a port. Is this clear? Okay, so you can understand that IO port is address of the IO device. I told you that every IO device has an address. So you can understand like this, that IO port, that is the address of the IO device. Every IO device has an address. So IO port, that is your address of IO device. So remember, this IO port, this is the address by which CPU can communicate with the IO device. So in simple words, remember, IO port means address of the IO device. Okay, for example, your USB port, your pen drive. Okay, where do you insert the pen drive in your computer? So you can see, IO port means the physical point at which the device is connected to the computer. Okay, that is called port. And remember, address of the IO device, okay, that is your IO port. So in simple words, you can understand like this, that IO port means address of the IO device. So if the CPU want to communicate with some IO device, then it will generate the IO address. Okay, and that is same as port number, IO port number. Okay. Now, one more thing I want to tell you, that is, I told you that in the interface we have different registers. Yes or no? Let's assume you have mouse. Okay, so that mouse is connected to mouse interface. In the interface there are different registers. For example, data register, status register. So there are different registers in the interface. These registers, do they have address? These registers, do they have address, or only the interface has the address? Can anyone tell me? These registers, do they have address? Tell me. Think about it. Let me know. Just think about it. I am asking that these different registers we have. in the controller, in the device controller, or I can say in the device interface. These are different registers. For example, your buffer, for example, status register. Okay, so these are different registers that we have. Now tell me, do they have address? For example, this buffer, does it have address? This status register, does it have address? Let me tell you the answer. Yes, they have address. Okay, they also have address. So remember, okay, each register has an address. And if you want the accurate definition of port, if you want the accurate definition of port, then that is, port is basically the address of register. Okay, is this clear? For example, maybe the address of this register is 500, address of this register is 501, address of this register is 502. Are you getting my point? Every register has address. Now you might be thinking, sir, why every register has address? See, very simple. If the CPU wants to read the status, if the CPU wants to check whether the data is ready or not, if the device is ready or not, then the CPU will fetch this. Yes or no? Agree? See, there is CPU. If the CPU wants the status of this device, okay, whether the device is ready or not, then the CPU, what it will do, it will fetch this status. This status will go to the CPU via databus. Yes or no? Via databus. So this is what I'm saying. Let's assume this is the CPU, and the CPU wants to know the status of this device, of this interface. Basically, the CPU want to know whether the device is ready or not, whether the data is ready or not. Then the CPU, what it will do, this status register, this will go to the CPU by databus. Okay, now this CPU, what it will do, this CPU, tell me what this will do. This CPU will check this bit. I told you, yes or no? This CPU will check this bit. Okay, whether device is ready or not, whether the data is ready or not. Okay, so the CPU will check this bit. Is this point clear? So you can easily see this status, this must have some address. Do you agree? If the CPU wants to fetch this status register, CPU wants to fetch this status register, then this register must have some address. Do you agree? Okay, similarly, if the CPU wants to fetch the data, the CPU wants to fetch the data, then this data register must have some address. So this is what I'm saying. Let's look at this point. So you can easily see, yeah. So read this point. What is IO port? IO port is simply the address of register inside the controller. Okay, is this clear? Let me know. IO port, that is simply the address of register inside the controller. Is this understood? Please tell me. Did you understand that inside the controller, inside the interface, you have device interface. In the device interface, we have different registers. We have data buffer, we have status register. So we have different registers in our device interface. Now, did you understand that these registers must have different addresses? Let me know. Please tell me. So remember the correct definition, that is, IO port is simply the address of register inside the IO controller. Okay, but most of the time I will use this word. For example, whenever I want to say address of IO device, then most of the time I will use IO port. But you should understand that registers inside the controller, they also have address. Okay, is this point clear? Inside the controller, these registers also have addresses. These addresses of the registers, these are called IO port. Address of the register is called IO port. Okay, and remember, but if very casually, remember, very casually, okay, I will use the IO port to say that address of IO device. Okay, but you must know that the accurate definition, if you want the accurate definition, then the IO port, that is address of the register inside the controller. The status register has an address. Okay, maybe status register has address 501. Data register buffer has address 500. Okay, so the registers inside the controller, they have addresses, and this is called IO port. Okay, agree? Clear? Let me know. So very simple point. So you can see that the CPU will access the internal registers of controller through what is called IO ports. So if the CPU want to access, for example, status register, then what the CPU will do? The CPU will access the internal registers, okay, using IO ports. Because what is IO port? This is address of register inside the controller. Okay, let's see this example. This example I found in the Oxford course, Oxford University Computer Organization course. Okay, so you don't have to understand this code. What I want to tell you, I just want to tell you that you can easily see there is port 500. Okay, this is a data buffer address. Is this clear? Let's assume there is a device. So there is a IO device. Okay, in that IO device will have a data controller, device controller. Yes or no? Every IO device has a device controller, or I can say device interface. Okay, in this device interface, you can see the data buffer. The buffer address is 500 and status register address is 501. This is what I want to tell you. You don't have to read this code, okay? But what I want to tell you is that status register has location address 501. I can say this is the port number of status register, okay? And what the port number of the buffer data register, that is 500. Okay, is this clear? So this is the idea. Now you can see we can read the status. I told you the CPU can read the status. So you can see we are reading the status here. The CPU is executing this command. Look at this command in 501. What it means? In means input. In means input. 501 means input, means basically this status register location is 501. So here what we are doing, input 501. That means CPU is reading the device status word. Okay, is this clear? Input 501 means the CPU is reading the status register which is at the location 501. The status register location is 501. So CPU is reading the device status. Okay, and here what is this? Look at this. What is this? Out 500. What this means? The CPU is outputting, the CPU is storing the data at this address. Okay, at this address, what we have? We have the buffer. Yes or no? We have the buffer. So at this address, the CPU is storing the data. So you can see out 500 means write in the device. The CPU is writing in the device. The CPU is storing data at this location. And at this location, what we have? We have data register, or I can say buffer. Okay. So overall, this is the point I want to convey, that the registers inside the controller, they have address, and that is called IO port. So the CPU will access the internal registers using IO port. Every register has an address that is called IO port. Okay, clear? Let me know. So very simple point. Now one more thing, you can easily see. Let's assume there are multiple IO devices. Let's assume I have some IO devices. Let's assume 4 IO devices we have. Okay. So if I have 4 IO devices, then I can say there are 4 port. Okay, there are 4 port. So these are the port. Remember this is port. Let's assume this is port A, or I can say IO device A. This is port B, this is port C, this is port D. Okay. Remember, here the IO device is connected. Here the IO device is connected. I can say this is IO device 1. Okay, here IO device 2 is connected. And here IO device 3 is connected. Here IO device 3 is connected. And here IO device 4 is connected. Okay, is this clear? And what are these? These are port. So this is your, I can say port. Port A, B, C, D. Is this clear? Now, what the CPU will do? If the CPU want to access these devices, then what the CPU will do? Please tell me. The CPU will generate IO address. Yes or no? The CPU will generate IO address. So you know that memory has a decoder. Do you agree? Main memory has a decoder. Yes or no? Address decoder. Main memory has an address decoder. Similarly, here we have IO address decoder. Similarly, this is IO address decoder. Okay. If the CPU want to access, for example, let's assume CPU want to access this IO device 3, then what the CPU will do? CPU will generate the address. Okay. Let's assume CPU will generate the address. So here IO address will be there. Here CPU will generate IO address. Okay. And then what will happen? Depending on the IO address. So you can see, depending on the IO address, these ports will be activated. Okay. Is this clear? Depending on the IO address, these ports, they will be activated. Okay. So you can see, depending on the, so you can see this is the enable signal. Okay. So you can see, depending on the address, one of these will be activated. Okay. So if the CPU want to interact with IO device 2, then what the CPU will do? CPU will generate the address of this port, or I can say the CPU will generate the port number B. Okay. Is this clear? The CPU will generate port number B, that is your IO address. And depending on the address, this IO decoder, this IO address decoder, okay, depending on that, you can see this will be activated. Okay. So this is a very simple diagram you can easily see here. So there is IO address which is generated by CPU. There is IO address decoder, and these are the IO devices, or I can say these are the ports. Okay, and these IO devices are connected to the ports. Yes or no? This IO device is connected to this port. This IO device is connected to this port. So very simple, the IO address, and depending on the address, one of them will be activated. Okay, and there is data bus also, that is also connected to the device. This that is also connected to the ports. So you can see there is data bus also. Okay, so very simple. So can you notice that communication with IO, that is similar to communication with memory so far? Can you see the similarity? If I want to, if the CPU want to communicate with main memory, then what it will do? It will generate the address. Similarly, it is generating the address of IO device. Yes or no? If the CPU wants to store the data, or if the CPU wants to read the data, then those things also the CPU can do with the IO device. The IO device, if this is input device, then the CPU will read the data from the IO device. And if the IO device is output device, then CPU will send data to the to the IO device. Yes or no? So very similar. Remember, CPU will communicate with main memory the same way CPU can communicate with IO devices. Okay, all these things will come into picture. Your address, the device address. Okay, the CPU want to communicate with some IO device, then the address of that IO device will be generated. Okay, that address the CPU will send on the address lines. Yes or no? So you can see the CPU will put the IO address on the address lines. And if the CPU, let's assume the CPU want to send data to some output device, the CPU want to send data on the speaker. Let's assume IO device is speaker, which is output device, right? So the CPU want to send data to the speaker. Then what it will do? It will put the data on the data lines. Okay, yes or no? And it will put the control signals on the control lines. So very simple. What I'm saying that very similar. We have like CPU communicates with memory, very similar to that, CPU will communicate with IO devices. Okay, is this clear so far? Let me know. All the concepts so far, are they clear? Please tell me. Now the next concept is connecting IO devices to system bus. Now we will see how to connect all the IO devices, how to connect them to the address lines, to the data lines. This is our next topic, connecting IO devices to system bus. So there are two ways, let me tell you. There are alternative ways of connecting IO devices to address lines, to data lines. There are alternative ways. These are memory mapped IO, and another is IO mapped IO. So one is memory mapped IO, another is isolated IO, or you can call it IO mapped IO. So these are two different ways to connect IO devices with the address bus, or I can say these are different ways to connect IO devices with the system bus. Okay, or you can say that these are the different ways how the IO devices are addressed. Okay, so you can see, if someone asks you, determine how the devices are addressed, the IO devices, the peripherals, how they are addressed. Okay, how they are given address, then there are two ways. One is memory mapped IO, another is IO mapped IO. Okay, so let's see the first, that is memory mapped IO. Let's understand this. The name itself is telling you memory mapped IO. Memory mapped IO means IO is mapped on the memory addresses. Memory mapped IO means IO, all the IO devices, they are mapped on the memory addresses. Means they are given the addresses, all the IO devices, they are given the addresses from the memory address space. From the memory address space, IO devices are given the address. Okay, so let's read the definition. What is memory mapped IO? The name itself is telling you memory mapped IO means IO is mapped on the memory address space. What it means? It means that with memory mapped IO, there is a single address space for memory locations and IO devices. Okay, what it means? It means memory mapped IO uses the same address space for memory and IO devices. Let's understand this. Let's assume that you have CPU and the CPU generates, let's assume 3-bit address. Okay, let's assume there are three address lines. Is this clear? Let's assume there are three address lines, A2, A1, A0. So you have three address lines. Means CPU is generating 3-bit address. Clear? Now, when the CPU is generating 3-bit address, then tell me the address space will have how many locations? Let me know. The address space, the CPU is generating 3-bit address, then the memory address space. Okay, this is memory address space. So the memory address space will have how many addresses? There will be total 8 addresses. Yes or no? So you can see there will be total 8 addresses. This address, this address, this address, 011, 100, 101, 110, and 111. So you can see these are the addresses. Okay, very simple. So CPU is generating 3-bit address. There are three address lines I can assume. that in the system bus there are three address lines. Then what are the memory address space? This is the memory address space. These are the addresses. Now, what this memory mapped IO says? Memory mapped IO says that memory and IO devices have the same address space. Have the same address space. What it means? This same address space is used by memory and IO devices. Remember, this common address space is used by memory and IO devices. For example, what I can do? I can use these locations for memory. Okay, these memory addresses. Remember, these addresses I can use for memory, and these addresses I can use for IO devices. This is what I can do. Okay, is this clear? Let me know. So these addresses, remember these addresses we are using for IO devices. I told you every IO device has an address. Okay, so you can see in the memory mapped IO, what we do, the memory and IO devices, they have the same address space. So you can see this is the address space. Okay, in this address space, these addresses we can assign to the main memory. Means when the CPU will generate this address, then what it means? When the CPU will generate this address, then main memory location will be accessed. Yes or no? The location of main memory will be accessed. But when the CPU will generate this address, then what will happen? Then IO device will be accessed. Okay, is this clear? So remember, main memory and IO devices, they have the common address space. Let me know, is this clear? So remember, memory mapped IO, that simply means that we have same address space for both memory and IO devices. This is your memory addresses, or I can, sorry, this is the address space. These are the addresses. Now in these addresses we can use for main memory, and these addresses we can use for IO devices. So they are basically sharing the address space. This is the address space, IO devices and main memory, they are sharing it. Okay, for example, what we can do, maybe this address, maybe this address we can give to mouse, maybe this address we can give to keyboard. Okay, and maybe this address we can give to disk. So what is the address of disk? If the CPU wants to access the disk, then what the address generated by CPU? If the CPU want to access the disk, then CPU will generate 111. And if the CPU want to access the main memory, then CPU will generate these addresses. Okay, these addresses the CPU will generate. Is this point clear? So very simple point, that in the memory mapped IO, we use the same address space for both memory and IO devices. Like this we can do. Okay, so this is the simple point. Now, for example, here, see this example. So each device, remember, each device, each IO device is assigned a specific memory address. Okay, clear? So if the CPU want to communicate with that IO device, then what the CPU will do? CPU will generate that address. For example, if the CPU want to communicate with mouse, then CPU will generate this address 101. For example, let's assume the printer. Let's assume the printer has this address, this memory address. Okay, in the memory mapped IO, let's assume the printer has this memory address. Now, if the CPU want to communicate with printer, then what the CPU will do? The CPU will generate this address. So when the CPU will generate this address, it simply means that CPU is accessing the printer. Okay. Now let's assume that CPU is putting this address on the address lines and some data on the data lines. Then what will happen to that data? See what I'm saying? I'm saying CPU is putting this address on the address lines. Means CPU want to access the printer because this is the address of printer. And CPU is putting some data on the data lines. Then what is that data? So that data is basically input to the printer. Yes or no? That data, that is input to the printer. So very simple. That data will go to the printer. You can see. So that data is input to the printer. Okay. Is this clear? So far, is this point clear? Now tell me one more thing. Since we are using the same address space for IO devices and main memory. So your main memory address space, remember, this is your main memory address space. In this address space, so this is the address space. Let's assume in this address space, I told you that some addresses will be used by main memory. Yes or no? For example, let's assume these addresses, all these addresses are used by main memory. These are the addresses used by main memory. These are the addresses of main memory. Okay. And these are the addresses of IO devices. These are the addresses of IO devices. Addresses of IO devices. Now you tell me one thing. If the IO devices, they are sharing the main memory address space, right? So do we need some other instruction, some special instruction for IO devices, or can we use the same memory instructions? What I'm asking, let's assume the CPU, this is our CPU. You want to access this main memory location. Then what is the instruction CPU will execute? The CPU want to access this main memory location. Okay, CPU want to access this main memory location. Then what the instruction CPU will execute? CPU will execute load. Yes or no? Load instruction. If CPU want to store some data here, let's assume CPU want to store some data here, then CPU can execute this instruction store. Yes or no? Or CPU can execute this instruction move. So do you understand that these are basically memory instructions? Yes or no? Remember, these are memory access instructions. Memory access instructions, right? Okay, if you want to access the main memory, then these are the instructions. But you can notice IO devices are sharing the address space of main memory. This is the complete address space, and the IO devices are sharing the main memory address space. So these same instructions we can use for IO devices also. Is this point clear? Let me know. In the memory mapped, these same instructions we can use for IO devices also, because IO devices are sharing the address space of main memory. Okay, so you can see same instructions we can use. Remember, we can use for output. Same instructions can be used can be used for IO devices. Okay, for example, if I want to read IO device, okay, let's assume this is a input. Let's assume this is some input device. Now tell me, if I want to read this input device, maybe this is keyboard. Keyboard is an input device, right? Okay, so let's assume this is a keyboard. Okay, then tell me, if I want to read from keyboard, then what instruction I can execute? Let me know. Let's assume this is the address. The address is, let's assume, 100. Now you tell me, if I want to read from the keyboard, I want to read from the keyboard, then what instruction the CPU can execute? The CPU can execute load 100. Yes or no? Load 100. Agree? Okay. If you want to store the data, then what you can do? Let's assume there is a device. Let's assume here you have hard drive, or I can say printer. Then what the CPU can do? CPU can do store 101. Okay. Is this clear? Let's assume this address. Okay, this address is printer address 101. This is the printer address. If this is the printer address, then what the CPU can execute? CPU can execute store 101. Okay, is this point clear? So remember, CPU can execute like this: load 100 means you are loading the data from the keyboard to the CPU. Okay, yes or no? Or you can execute store 101 means you are storing the data, you are sending the data from CPU to the printer. Okay, is this clear? So like this, we can use the same memory instructions to access the IO devices also. Is this point clear to everyone? Please tell me. So you can easily see the same instructions we can use for main memory and IO devices. If you want to access main memory, or if you want to access the IO devices, the same instructions we can use, like load, store. These memory instructions we can use to access the IO devices also. We don't need, remember, there is no need of special instructions to handle IO. Okay, if I want to take input from IO device, I don't need a special instruction. I don't need a new instruction. I can use this load instruction. If I want to send data to the IO device, then I don't need a special instruction. I can use this store instruction. Okay, so very simple. The same instructions you can use for accessing main memory and also for accessing IO devices. Okay, so very simple. Now let's move on. So what is the disadvantage? Tell me, can anyone tell me what is the disadvantage of memory mapped IO? I told you the advantage. What is the advantage? That we don't need special instructions. We don't need new instructions. These same memory instructions, load, store, move, these same memory instructions we can use to access the IO devices. Okay, if you want to take input from the IO device, you can use load instruction. If you want to send data to the IO device, if you want to send output to the IO device, you can use store instruction. So that is the advantage, that we can use same instructions to access the main memory, also to access the IO devices. But what is the disadvantage? The disadvantage is that the main memory is not using the complete memory address space. Yes or no? Main memory is not using the complete memory address space. Is this clear? So you can see the disadvantage. Look at the disadvantage, that is, we have reduced memory space. Yes or no? We have reduced memory space means the main memory is not using the entire address space. So we have reduced main memory address space. For the main memory, we have reduced the space. Is this clear? Please tell me. Did you understand? So you can easily see this is your main memory address space. There are 8 addresses. Okay, but in this memory mapped IO, what we are doing, this same address space is shared by main memory and IO devices. So you can see for the main memory, the address space is reduced. So this is the disadvantage. Okay, so you can see reduced main memory address space. Now let's move on. Now let me tell you, for example, let me give you one example what actually happens in the memory mapped IO. Okay, and try to understand this example. Memory mapped IO. First, let me clear some misconception here. Okay, see, some students what they think that, sir, this is your in the memory mapped IO. Let's assume you have 3 addresses. The CPU is generating 3-bit address. Let's assume the CPU is generating A2, A1, A0. This is what CPU is generating. Okay, then there is a main memory address space, right? Okay, yes or no? There is memory address space. Okay, address space. Let's call it MAS. Okay, let's call it MAS. Then there are total how many addresses? There are total 8 addresses. Yes or no? There are total 8 addresses. Now, which diagram is correct? This is what I'm asking. See, I'm asking which diagram is correct. 001 and so on. There is okay 100 and there is 101, 110 and 111. So these are the addresses. Do you agree? These are the addresses. And let's assume that I'm creating like this. See, this type of diagram I can also create 000, 001 and 111. Okay, now tell me which diagram is correct. I told you that in this memory mapped IO, what the IO devices will do, they share the address space of main memory. Yes or no? So what I told you that let's assume that these addresses means memory address. Okay, these addresses means memory address. Let's assume these addresses means memory address, and let's assume these addresses means IO devices. For example, this is the address of mouse. Okay, this is the address of mouse. This is the address of printer. This is the address of hard disk. Okay, is this clear? So this is the correct diagram. Agree with me that these IO devices, they are sharing the address space. Means these addresses are memory addresses and these addresses are IO devices addresses. Okay. Some students what they think that this is the main memory cell and here we are putting the printer. Here we are putting the printer. That printer is put here. Okay, printer is mouse is put here. If okay, so this is not what happens. Are you getting my point? See, some students think that okay, this is where we are putting the mouse. No, we are not putting the mouse here. We are not putting the mouse here. Some students think we are putting the printer here. No, we are not putting the printer here. What happens? This is what happens that let me tell you the exact picture. The exact picture is like this that the main memory has only these addresses. Okay, 001, 010, 011, 100. So these are the addresses of this is the main memory. Means main memory has only these addresses. This is the main memory. Okay, these are the addresses of main memory. And the remember, these addresses, very simple. These are the addresses of IO devices. For example, this is the address of mouse. Are you getting my point? This is the address of mouse. Let's assume there is mouse here. This is the address of mouse. Okay, is this clear? Similarly, 110, this is the address of printer. And similarly, 111, this is the address of disk. Okay, is this clear? So remember, IO devices are sharing the address space. They are not sharing, I can say, the main memory. They are not sharing the main memory. They are sharing the address space. Again, I'm telling you, the IO devices are sharing the address space. For example, if you have 3-bit address, then there are 8 addresses in the address space. Okay, in the address space, we have 8 addresses. Now, these IO devices are sharing the address space. Okay, so main memory and IO devices, they share the address space. Okay, is this clear? So you can understand like this that these are the addresses of IO devices. Okay, now also understand this important point in the memory mapped IO. Let's assume the CPU is generating 16-bit address. Okay, let's take one example that this is your CPU. The CPU is generating how many address lines? Let's assume there are 16 address lines. Means CPU is generating 16-bit address. Okay, if there is 16-bit address, how many addresses will be there? Can anyone tell me? If there is a 16-bit address, then how many addresses will be there? Total 2 power 16 means 64 KB. Yes or no? Okay. If all the addresses we use for main memory, then how much main memory we can have? If all the addresses we use for main memory, then how much main memory, maximum how much main memory I can have? 64 KB. Agree with me? So very simple point. CPU is generating 16-bit address. If you use all the addresses for main memory, then we can have 64 KB main memory. Okay. But in the memory mapped IO, the IO devices will also share the same address space. So can we have 64 KB main memory? The IO devices will also share the same address space. So can we have 64 KB main memory? No, we cannot have. Yes or no? So we will have less. Yes or no? We will have less memory. So let's assume that you have three main memory modules. Let's assume this is memory module M0, this is memory module M1, and this is the memory module M2. Okay, let's assume this is 16 KB, this is also 16 KB, this is also 16 KB. Is this clear? So let's assume these are the main memory modules. Okay, so very simple point, these are the main memory modules, and the remaining addresses, what about the remaining addresses? What about the remaining addresses? Remember, there are total 2 power 16 addresses. Okay, so if you use all the addresses for main memory, then we can have 64 KB main memory. But we also have IO devices, and in the memory mapped IO, the IO devices will share the address space of main memory. So the IO devices will share some of the addresses. Then in that case, we cannot have 64 KB main memory. Let's assume this is our main memory. We have total how much? Tell me how much total? 48 KB main memory we have. 48 KB main memory we have. Okay, is this clear? Now there will be decoder. Okay, tell me, there will be decoder. You already know there is an address decoder. Yes or no? You already know there is a memory address decoder. So there is an address decoder. This you already know that when the CPU will generate the address, then there will be address decoder. Yes or no? So now this is your address decoder. Now in this address decoder, see, CPU is generating 16-bit and there is address decoder. So here you have CPU. Okay, and CPU is generating 16-bit address. Okay. Now you already know that there is address decoder, memory address decoder. Yes or no? So we have total 3 memory modules. So let's assume that we are using the MSB 2 bits, means we are using these 2 bits of the address. For example, A15 and A14. Okay, we are using the MSB 2 bits of the address to activate these memory. Yes or no? To access these memory modules. These are memory modules. This is main memory. This has 16 KB. This has 16 KB. This has 16 KB. Very simple. Now, let's assume we are using the 2 MSB bits of the address. This is your address, 16-bit address we have. Yes or no? So, this is our 16-bit address. This is our 16-bit address. Okay. So, what we are doing? We are using the 2 MSB bits of the address to access these memory modules. Okay, so you can easily see. So let's assume 0. Here I can say this is decoder. Okay, this is our decoder. So 0, 1, 2, 3. Now you can see that if I put 0, 0. Okay, if I put 0, 0, then what I will do? I will access this main memory module. This main memory module will be activated. This is enable. Okay, this is a, I can say enable. Okay, if I put 0, 1, then this main memory module will be activated. If I put 1, 0, then this main memory module will be activated. Okay. And finally, what about 1, 1? When we have 1, 1, then what will happen? Now let's assume I have 4 IO devices. Okay. Let's assume I have 4 IO devices. These are the port. These are the IO port. Let's assume these are the IO port. Okay. Or I can say this is the IO device 1. This is the port. Remember IO port. IO port for IO device 1. This is IO port for device 2. So these are the port numbers. Port. Okay, IO port for device 3. And this is IO port for device 4. Okay, is this clear? So you can easily see when we have 1, 1, when these MSB bits are 1, 1, then in that case we will activate these IO devices. There are four IO devices. You can see IO port 1, IO port 2, and so on. Let's assume this is A, this is B, this is C, this is D. Now in this situation, what we will do? Again, we need another decoder. Yes or no? Maybe. Okay, it is not necessary. It is not necessary that we use another decoder, but let's assume we are using this decoder. Let's assume there is another decoder. Okay, it is not necessary that we use the decoder. I am just explaining the concept that what is possible. Okay, it is not necessary that we have another decoder. Okay, but let me explain the concept that if these are 1 1, means in the address the CPU will generate the address. Yes or no? CPU will generate 16-bit address. Now if the MSB bits are 1 1, then what will happen? If okay, then this decoder will be activated. Yes or no? If these two bits are 1 1, then this decoder will be activated. Okay, and let's assume in this decoder, let's assume I'm using A13 and A12. Okay, I'm using A13 and A12 to select these IO ports. Okay, in this decoder, remember, in this decoder, I'm using A13 and A12 to select these IO ports. Then what I can do? Again, the same thing, 1 2 3 0 1 2 3. Okay, so you can see, okay, if these are 0 0, then this port will be selected. Yes or no? This port will be enabled. Okay, else this port will be enabled. If you have 1 0, then this port will be enabled. And if you have 1 1, then this port will be enabled. Okay, is this clear? So very simple point. Now you tell me, if I want to enable, if the CPU want to communicate with port number A, then what will be the address? If the CPU want to communicate with port number A, what will be the address? Let me know. What will be the address if the CPU want to communicate with port number A? The CPU want to communicate with this IO device, then what will be the address generated by CPU? Then the CPU will generate 1100, and these are don't cares. Yes or no? This is the address will be generated. Agree? Remember, address is 16 bits. The CPU will generate 16-bit address. Okay, but remember, if the MSB 4 bits are 1100, if these are the MSB 4 bits, then CPU is accessing device number A. Okay, yes or no? This IO device CPU is accessing. Similarly, if the CPU want to communicate with IO device B, then what the address generated by CPU? Then the CPU will generate this address. Okay, and remember, if the CPU will generate this type of address, okay, then IO device C. And if the CPU is generating this address, then IO device D. Okay, is this clear? Let me know. So you can notice that if the MSB 2 bits, if the MSB 2 bits are 1 1, if these two bits, look at these two bits, if the MSB 2 bits are 1 1, then it means this is a IO address. Is this clear? In the memory mapped IO, you can easily see if the MSB 2 bits are 1 1, then it means this is a IO address. Okay, is this clear? And otherwise, this is a memory address. So this is what I'm saying, that you have 16-bit address. So there are 2 power 16 addresses. Yes or no? The CPU is generating 16-bit address. So in the address space, remember, there will be 2 power 16 addresses. So if we do not use memory mapped IO, let's assume all the addresses are used for main memory, then we can have 64 KB main memory. Yes or no? But here we are using memory mapped IO, means the IO devices will share the memory address space. Yes or no? So if you want to access the IO devices, then these IO devices will share the main memory address space. Okay, so we cannot have 64 KB main memory. Okay, let's assume we have 48 KB main memory. So this is your main memory. These are the modules of main memory, M0, M1, M2. These are the, I can say, 16 KB, 16 KB, 16 KB. So you can see total we have 48 KB main memory we have. Yes or no? Now you can notice that in this address which is generated by CPU, in this address, if the MSB 2 bits are 1 1, okay, then what will happen? Then that is the address of IO devices. Yes or no? So you can easily see, if the CPU want to access device A, IO device A, then this will be the address generated by CPU, that will be 1100, then something something something. But you can see these 4 bits will be 1100. If the CPU want to communicate with device D, then CPU will generate this address 1111 and so on. Okay, is this point clear? Is the complete picture clear to everyone? Let me know. So this is your memory mapped IO. Okay, is this clear? So in the memory mapped IO, can I say that IO devices and main memory, they have the common decoder? Yes or no? Can I say, please tell me, can I say that main memory and IO devices, they have the common decoder? Yes or no? They have the common address decoder. They have the common address decoder. This is the first thing. What the second thing? They share the address space. Yes or no? IO devices and main memory, they share the same address space. Okay, some addresses are taken by main memory, some addresses are taken by IO devices. What is the another thing I can say in the memory mapped IO? In the memory mapped IO, what is the other thing I can say? Can you notice this IO device has multiple addresses? Can you notice this IO device has multiple addresses? How is it having multiple addresses? Can you tell me? How is it having multiple addresses? See, if I want to access IO device A, if I want to access IO device A, then remember the CPU will generate address. The CPU will generate this type of address where these 4 bits will be 1100, but the remaining bits can be anything. Yes or no? So basically, the remaining bits can be anything. All these addresses, these are the addresses of device A. All these addresses, they are the addresses of device A. Agree? Yes or no? All these addresses, they are the addresses of device A. Correct? Is this point clear? So remember, in the memory mapped IO, the IO device can have multiple addresses. Yes or no? In the memory mapped IO, the IO device can have multiple addresses. Okay, so this is the point. Another, you can notice from this diagram, you can easily notice that in the memory mapped IO, the IO device can have multiple addresses. Okay, so I hope all these points are clear. And because remember, the IO device and main memory, they are sharing the address space, right? Yes or no? So that is the reason same instructions you can use. Same memory instructions you can use to access main memory and to access IO devices. You can use load store instructions. Okay. So you don't need new instructions for IO devices. If you want to access IO devices, then also you can use the same memory instructions like load store. Okay. Is this clear? A student is saying, sir, I did not understand that multiple addresses. See here, if I want to access this device A, then which address I will generate? Which address CPU will generate? If the CPU want to access this IO device A, then what address CPU will generate? The CPU will generate, yes, 1100. Then here any bits, here you can put anything, yes or no? So for example, this address is address, this address means IO device A, this address means IO device A, this address means IO device A, this address means IO device A. Okay, is this clear? So IO device A has multiple addresses. So in the memory mapped IO, remember, let me explain this. You can easily see in the memory mapped IO, you can see each IO device has one or more addresses. Is this point clear to everyone? The first point. Is the first point clear to everyone? That in the memory mapped IO, each IO device is assigned one or more addresses. Okay, simple point. So we have already seen. Okay. And what about in the memory mapped IO? If I give you the address, if the CPU will generate the address, then the address will automatically tell you this is memory mapped address or IO address. Do you agree? If I give you the address, let's assume the CPU will generate the address. This is the address that is generated by CPU. Now, this CPU has generated this address, then automatically means this address, either it will be memory address or IO address. Okay, you don't need any other thing. Yes or no? You don't need any other thing. So very simple, that if the CPU will generate the address, then that address that address will be either memory address or it will be IO address. It cannot happen both. Is it possible that same address is for main memory also for IO device? Is it possible that the same address is memory address also, it is IO address also? Is it possible? This is not possible, right? This is not possible. So very simple point. So you can see memory mapped IO. In this, what we do, the same address space is used. You can see some of the main memory address space is occupied by IO devices. Okay, the same address decoder we use. Okay, so yes or no? Same address decoder we use in the memory mapped IO, and the IO devices and main memory, they share the address space, and the you can use the same machine instructions. Yes or no? Load store. Agree? So you can see the same machine instructions, the same memory instructions you can use to access the IO devices. So very simple point. We don't need separate. See this? We don't need separate instructions for IO. Okay, the same memory instructions we can use like load store. So that's it. This is the complete thing. So you can see this explanation is basically taken from NPTEL. Okay, what I explained to you, the complete explanation, that is actually taken from NPTEL. You can easily see this diagram that CPU is generating 16-bit address. Yes or no? This CPU, this is generating 16-bit address. Now you can easily see that These two MSB bits we are using so that we can access the main memory or IO devices. And here you can see that we have these three memory modules and these are the four IO devices. So this complete explanation I have already provided to you. You can check out this diagram. Okay. So anyway, all the points we have seen. Now let's move on. Now let's solve this question. This is ISRO 2018 question. Of the following, which best characterizes computers that use memory mapped IO? Computers that use memory mapped IO. Basically, the question is asking what is the definition of memory mapped IO. So tell me which option is correct. The first option is saying the computer provides special instructions for IO. Is it correct? Is it correct? In memory mapped IO, the computer provides special instructions for IO. No, the same memory instructions you can use. Yes or no? If you want to access IO, then the same load store memory instructions you can use. Yes or no? These same instructions you can use for main memory, and also these same instructions you can use for IO. So we don't need special instructions. Yes or no? So option A is wrong. What about option B? IO ports are placed at addresses on the bus and are accessed just like memory locations. This is not the definition of memory mapped IO. Sorry, sorry. What this is saying IO ports are placed at addresses on the bus are accessed just like memory locations. Yes, this is correct. Yes or no? This is correct because in the memory mapped IO, you already know that IO devices and main memory they share the same address space. Yes or no? Some of the addresses are memory addresses, and the remaining addresses these are IO addresses. So you can easily see IO ports are placed at addresses on the bus, and they are accessed just like memory locations. They are accessed just like memory locations. Yes or no? So option B, that is correct. What about the next? To perform IO operations, it is sufficient to place the data in address register and call channel to perform the operation. So this is not the definition of memory mapped IO. IO can be performed only when memory management hardware is turned on. This is also not correct. So the answer will be option B. Is this point clear? Please tell me. Let me know. A student is saying, sir, for IO ports, don't we need IO interface? Yes, we need. Yes, for every IO device, there will be IO interface. Yes or no? But I'm saying that the address will be shared. The IO devices, see, IO device does not have an address. IO interface has the address. Yes or no? Every IO device is not connected to the system bus directly. IO device is connected to the system bus via interface. Okay, I already told you what is port number, what is interface. Okay, so this interface has the address. The CPU will communicate with the interface. So when the CPU is generating the address, it is generating the address of the IO interface. If I want to communicate with keyboard, if the CPU want to communicate with keyboard, then CPU will generate the keyboard interface address. Is this clear? CPU is going to generate keyboard interface address. But what I'm saying that in the memory mapped IO, the IO devices addresses and the memory addresses, they are shared. Basically, IO devices and main memory, they share the same address space. So you can easily see that. Look at option B. This is saying that IO ports are placed at addresses on the bus and they are accessed just like memory locations. Okay, these IO devices, or I can say IO ports, they are accessed just like memory locations. Yes, this is the definition of memory mapped IO. Okay, is this clear? So very simple, the answer will be option B. Now let's study what is IO mapped IO, or I can say isolated IO. What the definition of this? The name itself is telling you this is IO mapped IO, means basically IO has different address space. Okay, see, in the memory mapped IO, the IO is sharing the address space with main memory. But here we have IO mapped IO, means IO devices have separate address space. That is the reason this is called isolated IO, because IO devices have separate address space. So let's see the definition. In the IO mapped IO devices have separate address space. They have their own address space, which is different from memory address space. Okay, IO devices have separate address space. This is different from main memory address space. That is the reason we call it isolated IO, because the IO devices have separate address space. Isolated IO maintains an address space that is separate from main memory address space. Okay, in these systems, now notice one thing, that memory address space is different, IO address space is different. Okay, IO devices and main memory, they are not sharing the address space. Basically, they have different address space. Now, in this situation, can we use the same memory instructions to access the IO devices? If you want to access the IO devices, can you use the same memory instructions like load store? The answer is no. In these systems, remember, because IO devices have separate address space, in these systems, we need special IO instructions. These are in and out. Okay, these are in and out. So we need special IO instructions. These are in and out. Okay, in for if the CPU want data from the device, then in, and if the CPU want to output the data, then out. Okay, is this clear? So very simple. Now let's see. So what happens in this situation? Let me tell you that, remember, the CPU, let's assume the CPU is generating 3 bits. Okay, let me give you one example here. See, I am saying that let's assume you have 3 address lines, A2, A1, A0. Then what are the memory address space? How many addresses in the memory address space? Tell me. In the memory address space, how many addresses? If you have 3-bit address, then in the memory address space, how many addresses? There will be total 8 addresses. Okay, 8 addresses. Correct. And in the IO, what about IO address space? What about IO address space? What about that? How many addresses will be there in the IO address space? In the IO address space, how many addresses will be there? Let me tell you. Answer again, 8 addresses. Okay, see one thing. I am saying that main memory and IO devices, they have separate address space. Does it mean that they have separate address lines? Tell me. I am saying that main memory address space and IO address space, they are separate. They are separate. Means basically, if you have 3 address lines, or I can say if you have 3-bit address, then there are 8 locations in the main memory, and there are 8 addresses in the IO address space. See, understand the difference. When I say address space are different, it does not mean that they use different address lines. Are you getting my point? See what happens. Understand what happens. So this CPU is generating 3-bit address. Okay, this CPU. This is generating 3-bit address A2, A2, A1, A0. So 3-bit address this CPU is generating. Correct? Okay. Now, what will happen in this situation? In this situation, there will be memory address decoder. Yes or no? In this situation, here you have memory address decoder. Okay. See, let's understand this, that the computer, the CPU is generating 3-bit address. This is our 3-bit address. So in this IO mapped IO, okay, here you have 3-bit address. In this IO mapped IO, I told you that main memory and IO devices, they have separate address space. Then how much main memory we can have? Tell me, how much main memory we can have? We can have total 8 addresses. I can say 8 bytes. Yes or no? We can have 8 bytes main memory. Correct? So you can easily see we can have 8 bytes main memory. Do you agree? Let's assume this is your main memory. This is our main memory. Okay, so we can have total 8 bytes main memory. Correct? Do you agree? Okay, is this clear? So there is a address decoder that you already know, that you will give the address. You will give this address. You will give this A2, A1, A0. This address you will give, and depending on the address, these locations will be selected. Yes or no? Depending on the address, these locations will be selected. Correct? Like this. For example, if the address is 000, then this location will be selected. For example, if the address is 001, this location will be selected. If the address is 111, this location will be selected. Is this point clear? Please tell me. See, very simple point. Remember, we are discussing IO mapped IO. Means IO devices are not sharing the memory address space. Okay, the memory address space IO devices are not sharing. So the complete memory address space we can use. So if we have 3 bits, let's assume the CPU is generating 3-bit address, then remember there will be total 8 addresses possible. And remember, main memory can use the entire address space. Yes or no? Because IO devices are not sharing the address space of main memory. So the main memory is free to use the entire main memory address space. That is the reason if you have 3-bit address, then you can have 8-byte main memory. Yes or no? Is this clear? So there is main memory address decoder that is here. Okay. Now, remember the same address lines. The same address lines, what you can do, you can just put another decoder you can just put another decoder. Remember, the same address lines will be used. Okay, you have three address lines, the same address lines will be used, but you need another decoder for IO devices. So you need IO address decoder. Okay, is this clear? You need another decoder. Remember, you need a separate decoder for IO devices. Okay, in this decoder, again, what you will do, the same address. Okay, in this decoder also the same address, A2, A1, A0, the same address will go. Okay, and remember what you can do now. Total 8 IO devices you can put. Total 8 IO devices you can connect. For example, maybe this is the IO device, maybe this is the IO device 1. Okay, maybe this is the IO device 0. Okay, this is the IO device 7. Okay, is this clear? Please tell me. Is this understood? So far, is this point clear? So very simple, I am saying that the CPU will generate 3-bit address. Okay, remember this 3-bit address. If you give to the memory address decoder, then this memory location will be selected. This same 3-bit address, I can say this same 3-bit address is going here. Notice here, the same 3-bit address is going here, and the same 3-bit address is going here. Okay, is this clear? So very simple point, that this address, this 3-bit address, when it is going to memory address decoder, then one of the memory lines will be selected, one of the memory location will be selected, and this same address, this will go to the IO address decoder, then one of the IO device will be selected. Okay, is this clear? Now tell me, if I generate some address, for example, let's assume I generate 010, then what will happen? This memory location also will be selected, this memory location also will be selected, and this IO device also will be selected. Then there is a problem. Do you agree? Then there is a problem, right? Yes or no? Do you agree there is a problem, that the CPU is generating the address, either this is memory address or this is the IO address? Yes or no? CPU is not generating memory address and IO address simultaneously. No, either the CPU is generating memory address or the CPU is generating IO device address. Now, when the CPU is generating, for example, this address the CPU is generating, then you can notice this location will be activated and this device will be activated. Then there is a problem. So what is the solution? Let me tell you the solution. Will you basically, one solution you will be thinking, sir, we can use different address lines. Yes or no? You will be thinking, sir, one solution is use different address lines. Means, these for main memory use 3 address lines, and for IO devices use 3 different address lines. Okay, is this solution good? You might be thinking, sir, use different address lines for main memory, use different address lines for IO devices, but this is not a good solution. Why? Because there will be too many address lines. Yes or no? In the CPU, there will be too many pins, there will be too many system lines, I can say, address lines. Okay, so that is not good. Okay, that is definitely not good. But let me give you one very simple solution. Okay, the simple solution is this. All you need is just one control signal. See the simple solution. The CPU need to generate one control signal. Okay, the CPU need to generate one control signal, the CPU will generate, and this control signal is IO/M bar. Okay, this CPU will generate control signal. Is this clear? This control signal the CPU will generate, control signal, and this control signal is IO/M bar. Now what this control signal means? CPU generates control signal, this IO/M bar. What this control signal means, let me tell you. This is like this, that when this control signal is 0, then what we will access? If this control signal is 0, then what we will access? Then the address is memory address. Is this clear? Then access the main memory. Okay, is this clear? So when this control signal is 0, then access memory, and when this control signal is 1, then access IO device. Yes or no? Very simple. Just one signal you need. Okay, the CPU will generate this signal if this signal is 0, because remember M bar. Okay, IO/M bar. M bar means basically if the signal is 0, then you are accessing memory, and if the signal is 1, then you are accessing IO. So what the CPU will do? CPU will generate this signal. That's it. Okay, remember one more interesting thing. This signal, will enable either this decoder, also this decoder. This signal will enable these decoders. Now let's assume this decoder has, okay, for a moment, let's assume this decoder has active low enable. Okay, let's assume this decoder has active low enable. active low enable. Now tell me when this decoder should be activated. Just tell me. Let's assume this decoder. I am saying this decoder has active low enable. Active low enable. Okay, this is what I am saying, that this decoder you have, this is the decoder, and let's assume this decoder has active low enable. This is the enable signal, right? Okay, this decoder has this enable, this enable. This bubble means active low enable, correct? Okay, this bubble means active low enable. What it means? What it means? It means this decoder will be working, this decoder will be activated when this you apply the signal 0. Yes or no? Means this decoder activated, this decoder is active, this decoder is active when you apply the signal 0. Yes or no? When you apply the signal 0, because remember, this bubble simply indicates active low enable. Means this decoder will be active when this signal is low, when the signal is 0. Is this clear? This decoder will be active when the signal will be 0. That is the reason this enable, this signal is called active low enable. Means this signal will do its work when it is low, this signal will do its work when it is 0. So the decoder will be active when the signal is 0. Okay, is this clear? So now let's assume that both the decoders, these both the decoders, they are using active low enable. Okay, now you tell me when this decoder should be activated. Just tell me, very simple. The CPU is generating this signal IO slash M bar. This signal, this control signal CPU is generating. Now tell me when this memory address decoder, when this should be activated. This should be activated when this signal is 0. Okay, so what I can do, I can connect this directly here. Yes or no? Because when the signal will be 0, then enable will be 0. If the enable is 0, then this decoder will be activated. It means the memory location will be activated. Yes or no? Now, tell me when this IO address decoder should be activated. When this decoder should be activated when the signal is 1. Yes or no? When the signal is 1. So what I will do? What I can do? Tell me. Very simple. This is what I can do. I can just put an inverter. I can just put an inverter and then I can send it here. Yes or no? I can put a NOT gate and I can send it here. That's it. Now, did you notice what is happening? See, very simple diagram. Now, this is your IO mapped IO. This is your IO mapped IO. Did you understand IO mapped IO? This is IO mapped IO. See, interesting thing. Okay, just understand. See, CPU is generating 3-bit address. There are only 3 address lines. Remember, in your system bus, there are only 3 address lines. Okay, but remember these 3 address lines. Because of these 3 address lines, there will be 8 memory locations. Also, there will be 8 IO devices we can connect. Okay, is this clear? There will be 8 memory addresses. Also, there will be 8 IO devices addresses. Okay, now remember, this CPU will generate the address. Okay, now this address, either it can be memory address or it can be IO address. Now, how to differentiate? We want to differentiate. Basically, if the CPU is generating this address, let's assume the CPU is generating this address. If this is your address, then how to differentiate whether this is memory address or this is IO address? Yes or no? Okay, we are confused whether this is this memory address or is this IO address? Correct? Do you agree with me? So how to differentiate that whether this is memory address or is this IO address? How to differentiate? This is our question. Okay, and to solve this, what we are doing, we are using a control signal. Okay, the CPU will generate a control signal, this IO slash M bar. This control signal the CPU will generate. If this control signal is 0, then access memory. And if this control signal is 1, then access IO devices. Now, very simple, what we will do? This control signal we will connect to this decoder. Also, we will connect to this decoder. Okay, you can see. So this control signal we are directly connecting to this decoder. So you can easily see this decoder has active low enable. This is active low enable. So when the signal is 0, then this decoder will be activated. And that is correct. When the signal is 0, then we want to access main memory. Now, when the signal is 1, we are using inverter here. We are using NOT gate here. So when this signal is 1, then this will be activated. Okay, so that is correct. When this signal is 1, then we want to access IO devices. Okay, is this clear? So this is the solution. This is your IO mapped IO. So in the IO mapped IO, do we, tell me, Do we have different address lines for IO devices and memory? Do we have different address lines? No, we don't have different address lines. All we need is just this control signal. Okay, yes or no? This control signal we need. That's it. That's it. Now let me tell you one more interesting thing. In this IO mapped IO, what we do in this IO mapped IO, I told you that if you want to access main memory, then what are the instructions? If you want to access the main memory, then what are the instructions? If I want to access main memory, then the instructions are load comma store. Yes or no? Then the instructions are load comma store. These are the instructions. And if I want to access the IO devices, then what are the instructions? Then what are the instructions? If I want to access IO devices, then the instructions are in comma out. In comma out. Okay. Now let me tell you that what these instructions will do. Internally, what these instructions will do. This instruction what it will do, and this instruction what it will do. They will make this control signal equal to 0. Is this clear? Let me know. Is this clear? So remember these instructions. If the user is writing, okay, I am the user. Okay, in my program, if I'm writing this load, then what this load instruction will do? This will make this signal 0. This store instruction also will make this signal 0. Okay, and what this IO, what this instruction, what this will do? This instruction, what this will do? Tell me. This will make this signal 1. This will make this signal 1. So that's it. I hope you understood. So what I'm saying, see, you are the programmer. Let's assume you are writing a program. In your program, if you are writing load, then in your mind, what you want to access, tell me. What you want to access in your mind, tell me. You are the programmer, you are writing a program. When you are writing the program, you are writing this load. Then in your mind, you want to access the main memory. Yes or no? So that is the reason internally. Okay, internally, this instruction, this load instruction will generate this signal. Okay, is this clear? The load instruction will make this signal equal to 0. Okay, and similarly, you are the programmer, and let's assume you write this instruction in. Then you want to access the IO device. So when you write this instruction, then internally this signal, this control signal will become 1. Okay, so that's it. Is this clear? So very simple that in this IO mapped, what you need, what are the properties? Tell me, what are the properties that we have seen so far? Address decoder is same or not? The memory address decoder, IO address decoder, are they same or not in the IO mapped, IO? Let me know. The memory address decoder and IO address decoder, the decoders are same or not? Different decoder, yes or no? I've already told you. You can easily see different decoder, memory address decoder, IO address decoder. We have different decoders. So first of all, we need different decoders. Yes or no? Separate decoders. You can easily see here that we need separate decoders for memory and IO ports. That is one thing that we have already seen. I told you there is a new signal we need. What is that new signal? We need new signal to identify whether the address is memory address or IO address. If the CPU is generating some address, let's assume CPU is generating this address. Now, is this memory address or is this IO address? For that, we need a signal. What is that signal? That signal is IO slash M bar. That is your signal. This point also we have seen, agree. I told you that in this IO mapped, what we do, we have separate instructions for IO, that is in and out. This point also we have seen, correct? Okay. And the last point, the complete memory address space is utilized. Yes or no? In this IO mapped, the complete memory address space that is utilized. Yes or no? So that is also we have seen. So all the 4 points we have seen. Is this point clear? Let me know. All the 4 points are they clear? That in the IO mapped, in this, the complete memory address space we can use. The entire memory address space we can use for main memory, and there is separate address space for IO devices. Okay, what about address lines? The address lines are common or not? What about the address lines? Are they common? The address lines. Yes, address lines are common. Okay, there is only one signal. Yes or no? One additional signal we need. Other than that, we have common address lines and we have common data lines. Is this clear? We have common address lines. We have common address lines and there are common data lines. Is this clear? Let me know. So very simple point. And here we have this IO slash M bar signal. This is a control signal. Okay, and different instructions for IO, in comma out. These are different instructions for IO. And load comma store for memory. Load comma store for memory access. And in comma out for IO access. So that's it. Is this clear? Everything that we have seen, is that clear so far? What is the disadvantage? What is the disadvantage? Can anyone tell me? What is the disadvantage of IO mapped IO? The disadvantage is that we need special instructions. Yes or no? We need special instructions in comma out. So we need special IO instructions. What are those? Those are in comma out. So we need additional instructions. We need very simple. So this is one of the disadvantages, that to access IO, we need different instructions. To access memory, we need different instructions. This is the disadvantage. What the advantage? The advantage is that because IO and main memory, they are not sharing the address space. Yes or no? Their address space are separate. Their space is separate. So the entire main memory address space we can use for main memory. The complete main memory address space can be used for main memory. This is the advantage. Okay. So very simple. Let me ask you this question. The Pentium processor supports isolated IO. Does it mean it does not support memory mapped IO? Please tell me. Tell me the answer for this question. The Pentium processor that is supporting isolated IO. Does it mean that it does not support memory mapped IO? Let me tell you the answer. See, think about memory mapped IO for a moment. This memory mapped IO, does it need any special thing from the processor? See, IO mapped IO needs something special. Yes or no? What IO mapped IO needs? Just think about this. What IO mapped IO needs? I'm asking that what IO mapped IO needs. Look at IO mapped IO. Okay. Look at this system and look at this system. Memory mapped IO. Okay. And you tell me something very simple thing. In the IO mapped IO, what are the fancy things we need? In the IO mapped IO, what we need? What are the fancy things we need? We need control signal. Yes or no? This control signal we need. Yes or no? Yes or no? This control signal we need. Do we need this control signal in the memory mapped IO? Do we need this control signal in the memory mapped IO? No, we don't need. Yes or no? What else we need? We need in comma out. These instructions we need. These IO instructions we need. Correct? Okay. Do we need them here? No, we don't need. Okay. Additional decoder we need. Yes or no? Additional IO address decoder we need. IO address decoder we need. Do we need it here? The answer is no. So you can easily see in the memory mapped IO, we don't need anything from the processor. Yes or no? Yes or no? No. I can say we don't need any special treatment from the processor. Do you agree? No special consideration from the processor. No special treatment from the processor. No special treatment from processor. From processor. Okay. For example, For example, what this memory mapped IO will say, I don't need any special treatment from the processor. The IO mapped IO that needs this additional control signal. I don't need this control signal. This IO mapped IO needs in and out IO instructions. I don't need. I will use the load store. Yes or no? I will use the load store. You need additional IO address decoder. I don't need that. So basically, memory mapped IO, this needs no special treatment from the processor. Agree? Yes or no? No new instructions, no new control signal, nothing. Nothing. So that is the reason. Remember, memory mapped IO. That is the reason. That is the reason. So memory mapped IO is supported by every processor. Is this clear? Memory mapped IO is supported by every processor. Is this point clear? Memory mapped IO is supported by every processor. Now it is your choice whether you want to use it or not. Is this clear? Is it clear? Memory mapped IO is supported by every processor. Now it is your choice whether you want to use it or not. By every processor. Now it is your choice whether you want to use it or not. If you want to use it, you don't need anything extra. You don't need any new control signal. You don't need any new IO instruction. You don't need any new decoder. So remember, you don't need any new special treatment from the processor. That is the reason this memory mapped IO, this is supported by every processor. Now it is your choice whether you want to use it or not. Is this point clear? Did you understand this? Did you understand this point that memory mapped IO, this is supported by every processor. Every processor, each and every processor supports memory mapped IO. But it is your choice whether you want to use this facility or not. Okay, if you want to use IO mapped IO, yes, you can use it. But if you want to use memory mapped IO, that also you can use it. Okay, so this is supported by every processor. It is like this. Let me give you one analogy. Just consider this, then you will understand what I want to say. Analogy is like this. Assume that memory mapped IO, that is like walking. Okay, memory mapped IO, you can understand like that is like walk. Okay, that is similar to walk. Okay, and this IO mapped IO, that is like car. Okay, you need many extra things, correct? So let's assume that is like a car. Okay, is this clear? Now tell me, let's assume I have a processor. This is you. Okay, this is you. You are the processor. You are the system or you are the processor. Now you tell me. Now you tell me. Let's assume you are the processor and you have a car. Okay, let's assume you have a car means you are using IO mapped IO. Is this clear? Let's assume you are the processor and you have car means you are using IO mapped IO. Now you tell me, if you want to use memory mapped IO, can you do that? Are you getting my point? I am saying that you are the processor and you are using IO mapped IO means basically you have the car. Okay. Now, anytime if you want to use memory mapped IO, can you do that? After driving this car for 2 hours, if you want to walk, can you do that? Yes, of course. Yes or no? Everyone can walk. Okay, I can walk, you can walk, everyone can walk. Okay, but you can easily see. So it's like this. Every processor will support this. Now that is your choice whether you want to use it or not. Is this clear? Please tell me, did you understand? Every person can walk. Now it is your choice whether you want to use car or whether you want to use walk. Okay, maybe you want to use car. But I am saying if you have a car, then can you walk? This is my question. Did you understand this question? See, read this question. I am saying, read this question. The Pentium processor supports isolated IO, means IO mapped IO. Does it mean it does not support memory mapped IO? Please tell me. A student is asking, IO mapped IO is faster or not? That I will explain after some time. Okay, forget about it. This point, did you understand? Who is faster, IO mapped IO or memory mapped IO? Who is faster? I will tell you after some time. But this point, you try to understand what I am saying. Did you understand this point? That so the point is this, that memory mapped IO needs no special treatment from the processor. In the memory mapped IO, you don't need special IO instructions. Okay, for IO instructions, for IO access, you can use load store. Okay, you don't need any address decoder, extra address decoder. Yes or no? You don't need any extra control signal. So no special treatment from the processor you need. Okay, that is the reason. That is the reason I can say memory mapped IO is supported by every processor. Is this point clear? So you can see, for example, if you have a car, then does it mean you cannot walk? Of course, if you want, you can walk. Yes or no? So if the processor is using isolated IO, it does not mean that it cannot support memory mapped IO. Okay, this is the point. So if you have a car, even if you have a car, still we can use, still we can use, still we can use walk. Yes or no? Still we can walk. I can say like this, still we can walk. Okay, so it is our choice. It is our choice whether we want to walk or not. Our choice whether we want to walk or not. So this is the point I'm saying. So finally, the answer will be, does it mean it does not support? The answer is no. Okay, so read this. So this question actually I have taken from a standard book. Let me tell you. This question, this is an exercise question in a standard book of computer organization. This is a very nice question. Okay, that one processor is supporting isolated IO. Does it mean it does not support memory mapped IO? The answer is no. Okay, because remember, this memory mapped IO, read this statement. Memory mapped IO does not require any special consideration from the processor. Okay, read this. Memory mapped IO does not need any special consideration from the processor. Why? Because there is no need of special IO instruction. Okay, there is no need of extra decoder. So basically, very simple that this memory mapped IO, this does not require any special consideration from the processor. So all the processors, they inherently support memory mapped IO. Okay, so very simple. So finally, you can see if the Pentium processor is using IO mapped IO, then does it mean it does not support memory mapped IO? The answer is no. All the systems, remember, all the systems, they support memory mapped IO. Okay, simply because why? Simply because no extra support is required. Okay, you don't need extra hardware, you don't need extra decoder, you don't need extra control signal, you don't need any extra instruction. So there is no extra support required. That is the reason all the systems, they inherently support memory mapped IO. Now it is your choice which you want to use. Okay, is this clear? Please tell me. But tell me one thing, let's assume there is a system which is using memory mapped IO. Now can it use isolated IO? There is a processor, let's assume, and that processor is using memory mapped IO. Now, can it support IO mapped IO? Now, can it support IO mapped IO? The answer is no. Why the answer is no? Tell me. Why the answer is no? Just think about it. Let's assume I am the processor, I support memory mapped IO. But does it mean that I can support IO mapped IO? The answer is no, because if you want to support IO mapped IO, then you need extra decoder, you need IO address decoder, you need so extra decoder, you need extra control signal, you need this IO slash M bar, this control signal you need. Okay, you need extra instructions, special instructions for the IO access. Okay, in comma out, these special instructions you need. So a lot of new things you need. Are you getting my point? So remember the difference, you understand. Okay, if the processor is supporting isolated IO, then it can also support memory mapped IO because there is no special requirement. Okay, there is no special support needed. Yes or no? But if the circuit, if the processor is supporting memory mapped IO, then it does not mean that it can support IO mapped IO, because for IO mapped IO you need many extra support. Yes or no? Is this clear? So very simple. So this is the point. I hope you understood. Let me ask you this question. A system can use both memory mapped IO and IO mapped IO at the same time. Is it possible? Read this. A system, a processor, can use both memory mapped IO and IO mapped IO at the same time. At the same time, can you use both of them? The answer is yes. Okay, for different devices actually. So for some IO device I can use memory mapped IO, and so for some IO devices I can use IO mapped IO. So the answer is actually yes. Okay, for this question the answer is actually yes. And let me tell you, your modern, for example, your laptop. Okay, let me tell you, your laptop uses both memory mapped and IO mapped IO. Okay, so don't think that memory mapped IO and IO mapped IO, these are like you have to use one of them. It's not like that. Okay, in your system, in your computer, already both memory mapped IO mapped IO, both are used. Okay, for some IO devices memory mapped IO is used, for some IO devices IO mapped IO is used. Are you getting my point? In your system, in our computer, in my computer, okay, this computer that I have right now, in this computer, let me tell you, both memory mapped IO and IO mapped IO, both are simultaneously used. For some IO devices memory mapped IO is used, for some IO devices IO mapped IO is used. So the same system can support both of them. Is this clear? At the same time, same system can support both of them at the same time. Okay, is this clear? So for example, you can read this that both the strategies are used. Okay, like in this computer, okay, you can see in this architecture they use both of them. So you can see for different IO devices, remember. Okay, for some IO devices we can use memory mapped IO, for some IO devices we can use isolated IO. At the same time, for different IO devices we can use different mechanism. Is this clear? Let me know. Let's solve this question. This is gate 1987 question. Which is faster, data transfer between processor and IO device is usually faster in memory mapped than in IO mapped. In which scheme the data transfer is faster? Can anyone tell me? See the statement. This is GATE 1987 question. Data transfer between microprocessor and IO device that is faster in memory mapped scheme than in IO mapped scheme. So is this statement true or false? Let me tell you, this is a very simple question. Once I tell you one simple logic, you will tell me the answer. IO devices are slow or not? Which is slow? Memory or IO devices? Tell me. Which is slow? Memory is slow or IO devices are slow? Let me know. IO devices are slow, right? Yes or no? Your disk, your mouse, your keyboard. Okay, IO devices are slow. So you can easily see in the memory mapped. Look at this. In the memory mapped IO, all the IO devices they are treated like they are at the memory addresses. Yes or no? Agree? In the memory mapped IO, what we do? In the memory mapped IO, all the IO devices they are treated like they are the memory locations. Yes or no? The CPU is thinking that this IO device this is at a memory location, because in the memory mapped IO, memory and IO devices they share the address space. Yes or no? So the CPU is thinking that IO device this is at a memory location. Okay, so in the memory mapped IO, which instructions we use to access IO? If we want to do data transfer between IO device and microprocessor, if we want to do this data transfer, then in memory mapped IO, which instructions we use? Tell me, in memory mapped, which instructions we will use? We use these instructions: load, comma, store. Agree? Okay, these are the memory instructions. We use them. And in IO mapped, which instructions we use? In IO mapped IO, which instructions we use? We use in, comma, out. Yes or no? Are you getting my point? Please tell me. So is this point clear? So remember, if you want to do data transfer between IO device and microprocessor, if you want to do data transfer, remember, then in the memory mapped IO, you will use these instructions, and in the IO mapped IO, you will use these instructions. Which instructions are slow? Which instructions are slow? These are memory instructions. These are IO instructions. Which instructions are slow? These are memory instructions. Yes or no? These are memory instructions. I can say that these are memory instructions. Main memory is faster or IO device is faster? Tell me. Who is faster? These are memory instructions. So they are faster. So they are faster. Okay. And remember in, comma, out. They are IO instructions. They are IO instructions. They are slower. They are IO instructions and they are slower. Okay. Is this clear? So finally, this statement is true or not? Yes, this statement is true. Is this point clear? So memory mapped IO that is actually faster. Did you understand? Let me know. Remember, in the memory mapped IO, we use the same memory instructions to access the to do the data transfer between CPU and IO devices. Okay, see, very simple point. This is your CPU, this is your IO device. If you want to do data transfer between them, you want to do data transfer. Remember, this is what you need to do. You need to do data transfer between them. Okay. So for this data transfer, remember the memory mapped, what it will use? The memory mapped scheme. The memory mapped scheme, what it will use? Simple point that the memory mapped IO scheme, this scheme, what it will use? For this data transfer, it will use load, comma, store. Yes or no? Okay, it will use load, it will use store. So these instructions we will use. These are memory instructions. So they are faster compared to IO instructions. Yes or no? They are faster. They are faster comparing to in, comma, out. Okay, in, comma, out. Because they are memory instructions. This is a memory instruction. This is memory access instruction. Okay, this is memory access instruction. This is actually faster. So remember, these instructions are actually faster comparing to in, comma, out. Is this clear? Okay, let me know. And The same thing in the IO mapped IO, what you will do? In the IO mapped IO, what you will do for data transfer? For data transfer, tell me. So very simple. In IO mapped IO, what you will do? You will use in comma out. Yes or no? You will use in comma out. Okay, and they are slower. They are slower comparing to load comma store. Okay, yes or no? Because these instructions are IO access instructions and they are slower comparing to load comma store. Is this clear? So very simple that this memory mapped IO scheme, this is actually faster. Okay, is this clear? This memory mapped IO scheme, this is actually faster. So let me tell you, this is faster also. This memory mapped IO scheme, this is faster also. This is cheaper also, yes or no? Why this is cheaper? Can anyone tell me? Tell me why this is cheaper? This memory mapped IO, this is faster, we have seen. This is cheaper also because no extra requirement. Yes or no? You don't need extra hardware. You don't need IO address decoder. You don't need extra control signal. You don't need extra IO instructions. So this is cheaper also. This is easy to build. I told you every processor supports it. I already told you that every processor inherently supports this memory mapped IO. Every processor inherently supports memory mapped IO. So this is easy to build also. Okay, yes or no? This is easy to build. What else? What else? This will consume less power and this is physically smaller and this is supported by all systems. These are the benefits of memory mapped IO. These are the benefits of memory mapped IO. Is this clear? I have told you all the benefits. This memory mapped IO, this is cheaper because you don't need any extra hardware. Okay, you don't need any extra facility. Every processor supports memory mapped IO. This is faster, I told you. This is easy to build. Okay, this is physically smaller because you don't need any extra hardware. This will consume less power. So these are the benefits of memory mapped IO. Is this clear? So that's it. So did you understand memory mapped IO mapped IO, these concepts? Did you understand? Please tell me. So far, anyone has any doubt? Let me know. Let me know. Is this point clear? What is memory mapped IO? What is IO mapped IO? All the concepts, are they crystal clear to everyone? Please tell me. So this is enough for this session. What we have seen what are IO devices, input devices, output devices, some devices which are input as well as output. For example, hard disk, that is input device as well as output device. So first we have seen IO devices. Then we have seen that IO devices, these are also called peripherals. We cannot connect them directly to the system bus. What is the reason? Because there are many IO devices and they have different characteristics. Yes or no? They have different data transfer rate. Some IO devices are very slow. For example, mouse and keyboard, they are very slow. Some IO devices are comparatively faster. For example, disk, that is comparatively faster. Yes or no? And I told you that different IO devices, they have different sizes of data that they can transfer at one time. Okay, like for example, your keyboard can transfer one character at a time, or I can say one byte at a time. But the disk, the hard drive, that can transfer maybe kilobytes at a time. So you can see that the data format is also different in the different peripherals. So basically there are many reasons that different peripherals, the different IO devices, they have different characteristics. So that is the reason we cannot connect IO devices to the system bus directly. So what we need interface. Then I told you what we have inside this interface. Inside this interface we have registers, we have buffer register, we have status register. So some registers we have. Okay, why we use the status register? The status register will tell the CPU that the device is ready or not, the data is ready or not. Okay, yes or no? So this is the use of status register. And there is buffer also in the interface. For every IO device there is an interface, because the IO device we cannot connect to the system bus directly, so we need interface. So for every IO device, remember, so for every IO device, there is an interface. In the interface, we have some registers. We have status register, we have data register. Data register means buffer. Okay, I told you why we use the buffer, because the IO devices can be very slow. For example, let's assume the IO device is generating one bit at a time. Okay, but we cannot send this one bit to the CPU. Yes or no? What we will do? We will collect 16 bits. Let's assume data lines. There are 16 data lines. So we will collect 16 bits. Yes or no? So there is buffer. In the interface, there is a buffer. In that buffer, we can collect the data. Okay, the status register will tell the CPU whether the device is ready or not, whether the data is ready or not. Okay, so that is the idea of interface. We have seen what is interface. Then I told you what is port number. I told you what is port number. Port number means address of this interface, yes or no, or you can say address of IO device. Is this clear? Port number means address of interface, or you can say address of IO device. But remember I told you that inside this interface there are registers, status register, data register. So these registers, they also have different addresses. So actually the port number, if someone asks you what is actually the port number, the port number is the address of the register inside the device controller. Yes or no? Inside the device interface, the address of the register, that is port number. Okay. But casually we can say that port number means address of the device, or I can say port number means address of the interface. Okay. Is this clear? Then what we have seen, we have seen how to connect IO devices with the control bus, or I can say with the address bus. Yes or no? So basically how to connect IO devices with the system bus, this is what we have seen. Basically we have seen the addressing of IO devices, how to give addresses to the IO devices. For that there are two ways. One is memory mapped IO, another is IO mapped IO. In the memory mapped IO, what we do, the memory and IO devices, they share the address space. Yes or no? So there is same address space that is shared by main memory and IO devices. Some addresses they are memory addresses, and some addresses they are IO addresses. Okay. So very simple. In the memory mapped IO, because the address space is shared, okay, the main memory address space that is shared by IO devices and main memory. So IO devices don't need any special instruction for access. Okay. So you can use the same memory instruction, load and store, for data transfer. Okay. If the CPU want to read the read from the IO device, then it can use load instruction. If the CPU want to output to the IO device, it can use store instruction. So basically no new instruction, no fancy instruction, or I can say no special instruction is needed for IO access. Okay, so same load and store instruction you can use. Okay, and remember the same decoder you use, because the same address space, IO device and main memory, they are sharing the same memory address space. So that is the reason only one decoder is there, that is memory address decoder. Okay, you don't need IO address decoder. Okay, yes or no? So no extra hardware is needed. So that is the reason memory mapped IO, that is actually very easy to implement, or I can say that is supported by every processor. Every processor will support memory mapped IO, because there is no requirement. You don't need extra control signal, you don't need extra special instruction for IO, you don't need extra decoder. These things you do not need. So that is the reason this memory mapped IO, this is, I can say, this is supported by all the processors. Okay, so you can use it, or if you want you can use IO mapped IO. So this IO mapped IO, this is also called isolated IO. This is another scheme. In this scheme, what we do, the main memory address space and IO address space, they are different. Okay, remember address lines are not different. Address lines are same address lines you have. Okay, but when you have same address, now this can be either memory address or this can be IO address, because remember main memory address space and IO address space, they are different. Okay, so all the addresses you can use for main memory, also all the addresses you can use for IO devices. So remember, when I give you some, when the CPU will generate some address, this can be either memory address or this can be IO address. Now how to identify which address is this? The CPU will generate an address. How to identify this is memory address or this IO address? So what we need a special control signal, IO slash M bar. If this control signal, this is generated by the CPU will generate this signal IO slash M bar. If this signal is 0, then the address is memory address. If this signal is 1, then the address is IO address. Okay, so this control signal, this special control signal we use. Okay, and also there is memory address decoder and there is a separate decoder for IO. So there is memory address decoder for main memory and there is IO address decoder for IO devices. Yes or no? So you need extra decoder, you need also extra control signal you need, that is IO slash M bar, I told you. Okay, also because main memory address space and IO address space, because they are different, so you cannot use the load store memory instructions for accessing IO. So for accessing IO, you need some special instructions. Those are in comma out. Okay, so in comma out, these are special instructions to access IO. Okay, and load comma store, these are the instructions to access main memory. Okay, so this is your isolated IO. So remember, if you want to implement isolated IO scheme, then you need some additional support. Okay, you need additional control signal, you need additional decoder, additional hardware you need. Okay, also you need special instructions to access IO. So that is the reason, remember I told you memory mapped IO, that is faster, that is cheaper, that is easy to implement, and that is supported by all the processors. Okay, and remember, in your system, the laptop on which you are watching this lecture, that laptop is using memory mapped IO for some IO devices, and that is using IO mapped IO for some devices. So in the same system, you can use both the scheme. Okay, for some IO devices, you can use memory mapped IO, and for some IO devices, you can use IO mapped IO. Memory mapped IO, that is faster. Okay, why that is faster? What is the reason? That is the gate question. That why memory mapped IO is faster? Memory mapped IO is faster because what you can do, you can use this to access the IO. Remember, if you want to if you want to do data transfer between CPU and IO device, then you can use the same memory instructions. You can use load comma store, and you can do the data transfer between CPU comma IO device. These load comma store, these are the memory instructions, and memory is faster than IO devices. IO devices are very slow, so that is the reason. Remember, memory mapped IO, that is faster than IO mapped IO. So in your computer, for some devices, you can use memory mapped IO. For which devices will you use memory mapped IO? Tell me. The devices for which you need fast access. Yes or no? For the devices for which you need fast access, fast data transfer, if you need, then you can, for those devices you can use memory mapped IO. And the devices for which you don't need fast access, then for them you can use IO mapped IO. So in the same system, you can use both the schemes for different IO devices. Okay. So this is your complete chapter, and this is the complete summary. Please tell me, did you understand? Let me know. Please tell me, did you understand all the concepts so far crystal clear way? What is IO device? What is IO interface? What is port number? What is memory mapped IO? What is IO mapped IO? Everything is that clear? Let me know. Please tell me. Okay. Thank you, everyone. Is everything crystal clear? Whatever someone asks you, if someone asks you any doubt, any question, then can you answer from these topics? Please tell me. Okay. Thank you, everyone. In the next lecture, we will start IO data transfer techniques. Okay, in this IO data transfer technique, we have some different techniques. So those we are going to study, like programmed IO, interrupt driven IO, and direct memory access, DMA. So these are IO data transfer techniques. These we will study in the next lecture. Okay, thank you, everyone. Please share your feedback in the comments. Okay, thank you.